a word. Hello. I just want to welcome you to Haskell Symposium. Two few quick announcements. One is that as every year, we're going to have lightning talks. So I put one at the end of the day today and one tomorrow just before lunch. So there is a form at the webpage that you can register to give a lightning talk around 5 minutes if you want, and I will be around if you want to find me to help you with that. And the other is we're using Discord. We have a thread that is called Haskell. So if you are attending online and you have any questions, you can use that. Or if you want to talk about anything, you can use this thread. And that's all. I hope you enjoy the program that starts with our first keynote, which is Nicholas Wu. Most of us know Nicholas. He's a very active member of Haskell Symposium and the Haskell community. So he's at Imperial College, where he leads the functional research group. And before he was at Bristol and Oxford, where he did his PhD. And he works on category theory, semantics, and effects, obviously. And today he's going to talk about the evolution of effects.
Okay, well, hi everybody. It's a great pleasure to be here at Haskell Symposium. And indeed today I'm going to be talking about the evolution of effects. So this talk is not going to be your ordinary sort of Haskell-ish talk because there's going to be very little technical material here. This is actually going to be a history lesson for you. So let's see what it's going to be about. So I'm going to start with basically a history of the evolution of effects. So where do they come from? And starting with the history of programming languages, we're going to move on to the history of monads, effect handlers, and then possibly onto higher order effects. So that's the itinerary. So the caveat is that when I'm trying to do history like this, there's no way that I'm going to be able to talk about all of the history to the degree that I want to. There's just far too much to cover. And so I apologize in advance to anybody that I omit or anything that doesn't happen or if I do things in the wrong order. Surely there will be mistakes, but I'm doing my best. So I think the story starts really with this big dichotomy between functional and imperative programming that starts right at the beginning in computer science, and right at the beginning, by which I mean between Church and Turing. So of course, Church saying the way we should do computation is with lambdas, and Turing is saying we should be using assignment. And maybe there'll be an eternal separation between church and state. And since we are in the States, we have Jefferson on your $2 bill saying that the First Amendment was establishing that indeed there would be an eternal wall of separation between the two. And so since we're doing history, I thought I'd flash up on the left-hand side the Bill of Rights, where Article 3 is saying that there should be a separation between these two things. And then his explanation to the Banbury Baptist Association that indeed that's what they meant. So perhaps there's no hope of sort of making these two things come together, but we should try. So let's have a look at the history of programming languages. And it really is history because I'm going to take you back to 1666, and London is burning. And what's happening in 1666 isn't just that London is burning, but also that this chap here, Leibniz, has finished his PhD dissertation. And his dissertation is on the art of combinatorics. And it's about a proof of the existence of God from some fundamental principles, an alphabet of human thought, and the idea that all concepts are combinations of a core set of concepts. So he's thinking about modularity right from the beginning. So he writes a letter to one of his friends saying that one day he was on a ship on his way from London and the weather was bad and he had nobody to talk to apart from sailors. And so he decided to design a rational language. And so he's probably the first programming language designer as well, thinking about a way we could have a way of reasoning about metaphysics and morality. So that's a letter to one of his friends. And so yeah, maybe he was the first programming language designer way back then. Moving forward a bit at a different keynote elsewhere, Dubois-Reymond says something like ignoramus et ignoramibus, about the nature of knowledge and understanding. Basically, there's stuff that we do not know and that we shall not know. We should just not try. At the same conference, but a few years later, so this is 1930, Hilbert replies to that ending of a keynote with a different one, saying, "Wir müssen wissen, wir werden wissen." We must know, we shall know. And he tries to establish then, together with Ackermann, a whole bunch of open problems, and one of which is the decision problem, basically saying, given a question, is there a way of answering yes, no to that? And that opens up of course, the answer, which is no. Gödel introduces the incompleteness theorem and says, actually, there's no system of logic that you could produce which isn't complete in its own right. And then that idea is taken further by Church and Turing, who also say, yeah, we really have a problem here. There's no algorithmic way. There's no system that we could use or design that will solve this problem. And they do it independently and from two completely different perspectives, which I'm sure you all know about. Moving on a little bit furthermore, we get the work of von Neumann. So von Neumann picks up on the ideas of Turing and starts producing the first computer, or at least designing the first computer. And that's a very, very contentious statement because so many different claims to first computer come about. So the Americans have EDVAC in 1949, although they are, I think, scooped by the British, although silently and in secret the year before. But again, that's a highly contentious statement. And eventually, these computers need programming. And so fast forward a bit, you get the invention of Fortran by Backus. And this is a nice language because for the first time, you're not just putting instructions on a machine. You have equations, and you're able to sort of do some formula translations. But actually, Backus says that although people think that formula translations was a big contribution, his reflections tell us that he thinks it was actually about the structuring and organization of loops. So very early on, we're already seeing that the problem with programming isn't so much equational stuff. It's trying to understand effects. It's trying to understand sequencing and control structure. That's the difficult part that he thinks was the good contribution of Fortran. Meanwhile, in the functional camp, Lisp is created in '58 by McCarthy. And I hope you can see right up here, there's a bit of lag, that he has the lambda calculus in play right from the beginning. So we have a whole bunch of lambdas in the way the thing is designed. And he has this notion of conditionals. He has recursion. This thing's not working. He has recursion right from the go for factorials. And he also has the map list function appearing way back in the late 50s. So he's doing real functional programming with lists where head and tail are called car and cudder, of course, because they correspond to the machine instructions that you want to be using for these different constructions. And he even coins the term abstract syntax in '62. So these ideas kind of come together, or at least these people come together in '58 in the invention of ALGOL. So together with Peter Noir and a whole bunch of other people, they tried to design a language which is good for expressing algorithms. And so this language, Tony Hoare tells us, is a language that's so ahead of its time that it was not only an improvement on its predecessors, but also on nearly all of its successors. Including Haskell. That language was interesting because it's a very imperative language. And it's not long before, in '65, we see Peter Landin starting to work on how we can combine functional and imperative thought into a single paradigm. So he has this notion of what he would call applicative expressions, which is just a fancy way of saying he wants there to be some syntax for lambda expressions that isn't literally just writing lambda x dot blah. So he has let statements and ands and recursive lets and this sort of thing, and he thinks that that's a good way to go forward for the programmer. And he adds to it an assignment operation to come up with what he calls imperative applicative expressions and a machine that interprets these things. Okay. In '65, so shortly after, he shows a correspondence between ALGOL and these imperative applicative expressions and shows that there's correspondence between these two languages. So I think this is a nice establishment of the theory behind why ALGOL was really a functional imperative language from the go. So in '66, he writes a really important paper about the language ISWIM, which stands for If You See What I Mean. And this is called the Next 700 Programming Languages, and lots of other papers have the Next 700 named after this paper. And what this paper is really, I think, is it's a predecessor to Haskell. It has things like pattern matching, it has where clauses, it has garbage collection, and it has indentation sensitivity. So all sorts of things come out of this paper. I mean, some of these ideas are in other places, but this is where they all come together. So he writes things like this, which you could practically type into Haskell, and things would work. And it's an interesting piece of history because at the end of this paper, the questions that were asked during the conference have been transcribed, so you can see what the conversation looked like, and it's fascinating. Peter Noir says, regarding indentation. In many ways, I'm in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing. And if you've ever written a paper in Haskell, you know kind of what it means. But actually, I think it's a positive thing that the indentation is there because you can play around with it a lot more when you're trying to typeset things, but it is painful. The other thing that's interesting about this paper is that he equips the language with a whole bunch of equivalences for reasoning. So reasoning features very highly for him. He wants sub-expressions to be such that if two sub-expressions are equal somehow, then that means something about the greater expression, so there's a notion of congruence. He wants there to be equivalences between definitional things, so lets and wheres should somehow be equivalent. Built-in expressions like this is an if-then-else statement, there should be a way of understanding that equationally. And probably the thing that's most interesting to me is he wants that to be user-definable DSLs from the beginning. He wants users to be able to define their own small languages with equations, and ISWIM should be able to interpret those languages for the needs for the means that they're for. So DSLs are featuring very early on in this work, although again, that's not what they're called. So he says that these primitives should allow people to write equations between them. And I'm thinking about algebraic effects, which is all about operations and equations. And this is kind of being pointed to at a very early stage here. And around this time, structured programming starts to become very fashionable. So Burstel in '62 starts saying that we should be able to do proofs by induction over the structure of the input. It's an old idea even at this stage, but he makes it quite clearly here with these very early implementations of what looks like fold right and concat right from the get-go. And he's writing in ISWIM, and he shows that you could write a program for doing sorting via an intermediate tree. And this is the kind of thing that is very close to the Haskell you'd write in a sort of first-year course, I guess, and a proof of its correctness by induction. So these are some nice ideas coming together, and it becomes very fashionable in the '70s with a big book called Structured Programming, which is kind of famous at the time, where there are certain close analogies between the methods for using structured data and the methods for structuring the program which processes that data. And that sounds very familiar to those of us who like folding and catamorphisms and all that sort of thing. These ideas are being pointed to in the '70s. Back to the 700 programming languages paper, we have Landon saying that another really important thing that he wants to stress is this idea of denotational semantics. So he wants it to be such that the meaning of the whole is in terms of the meaning of the parts. And this is a critical point for him in the semantics that you give to the user-defined expressions. So how are we going to give a meaning to these things? Well, through a kind of structural induction. So essentially, he's hearkening forward to denotational semantics, which comes up a few years later. So denotational semantics, the paper there is in '71, which is something like 5 years later. And that's by Darrell Scott and Chris Strachey, where they have this equation right here in the middle that says exactly what I just said a minute ago, which is that the meaning of an expression is given by the meaning of its parts in composition. So this is a really critical idea that's coming out, again, all from the '60s. But actually, as I said, history is complicated, and this is definitely not completely true. It even came out before that, but that's a good place to start. So what I'm trying to get across at this stage is that the idea of the separation between computation as lambdas and computation as assignment is kind of murky from the beginning. Yes, there's a clear separation between the two, but there's a synergy between the two that's going on as well. People are thinking about how these things can be combined from the beginning. And so perhaps the question isn't so much how can we keep these things separate, but maybe there's a way of combining them together. And Landon has something to say about this in that same paper again. He says, ISWIM brings into sharp relief some of the distinctions that other authors are intended, such as adjectives such as procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. Here's a suggested classification and a new word. So the new word that he thinks that classifies all of these different paradigms is denotative. He thinks that denotative semantics should be the way that we think about programming languages, whether they be imperative or functional. That's the kind of the system that we want. So it's not so much about having a separation, but maybe some kind of synergy between side effects and field functions and understanding that synergy in detail. So what would denotative look like in the context of effects? Well, it means that we need to have a way of being able to reason about effects and how they're carried around and how they influence one another. And I think that the monads is a good way of doing that. So why on earth do we have a picture of a burrito? Well, there's somebody in the audience to blame for that, which is Brent Yorgi wrote in his blog in 2009 something about a fictitious person called Joe who's trying to learn monads and thinks that burritos is the right way to explain them. So even though it wasn't Brent himself who came up with monads, it was his fictitious Joe in his head, he's still to blame for this. He thinks that monads are like burritos. So I'm about to do a prehistory of monads, but monads in the context of this community. So in order to do that, I really need to go far back into ancient history of the memories of Haskell. And so I'm going to bring you to South Africa in 71,000 BC. What happened in 71,000 BC? Well, we have this rock. And this rock is actually the first object that we have that's been written on by any man at all. And so scientists have done some research on this rock. It comes from 73,000 years ago, and it was found in a cave somewhere in South Africa. And scientists have done some very careful analysis on this rock. It turns out that they've looked at the inscriptions very carefully, and they said there's no way this is coming up in nature. This was drawn with some crayons. And if you look very carefully at the inscription that's there, you can see that mankind has been striving for Haskell for a very long time. Actually, this is the real ancient history. I'm not sure if South Africa 71,000 BC is when this picture was taken, but here we have lots of different people from even in this room coming together, and there's a beautiful paper about history of Haskell being lazy with class, which goes through some of the history of Haskell in much more detail than I can now. And I just want to pick out that, according to that paper, obviously monads are one of the big inventions that came about, or one of the good things that came together for Haskell that worked well. So let's talk about where monads have come from to get a sense of that. So as I said, this talk is nothing to do with technical detail. It's a completely historical note. So let's think about monads and where they're from. So the kind of classic reference for all things category theory is this famous book, Categories for the Working Mathematician by Mac Lane. And he writes about monads in that chapter. And he has this little note that basically says, well, we didn't really realize how simple and important monads were for quite a long time. And he has two references for this. He says that he made a little note somewhere in some paper, and then they were expanded upon. So let's find out where he thinks monads were first referenced. So I did some digging around, and you come up with this paper. It's in French, and don't worry if you can't read it. Most of the slides you can't read what's on there anyway. The point I'm trying to make is it's in French, and it's difficult to read. And this tiny little four-liner is what he's referring to when he says that he invented monads or talked about monads from there. And if you read this carefully with the eye of category theory today, you might be able to see that he was talking about monads to a degree. But I think it's difficult to sort of establish that this is the beginning of monads. The beginning of monads comes much more clearly through the work of Godement, which again is in a French treatise on topology and sheaf theory. And if you look at that paper more carefully, you will spend hours, perhaps days, going through a whole bunch of French mathematics and find that after 260 pages, monads are not mentioned anywhere, except when you get to the appendix, and you think that's why this is the reference to this, because in the appendix, Roger Godement has these statements where clearly this is monads, right? So basically he has a definition of K being return and P being join hidden away, and he brings in what we now call the Godement calculus, which is the theory of what we call whiskering, which is a way of talking about natural transformations and functors in a very categorical language. But the equations A and B that we have here are exactly the monad laws that we would write today in category theory. So the first one is basically the identity laws that says something like return, which is K, is the identity of this monoid, and then the associativity is the second part, or at least the join laws come out from the second part with P.
It's 1958 again.
And it's 1950. Yes, exactly. Yes, indeed. Yeah.
When I was born.
Ah, okay. It's a good year. It's a good year. It's an important, very important year. I should have added that there as well. Sorry. So for years, monads were simply called the standard construction or the fundamental construction or simply just triples. So people have had troubles naming things for a very long time as well. And it wasn't until quite some time later that the term monad actually appears in this context. And that's by this chap, Jean Benabou, in 67, and he's starting to write about bicategories, of course. And this is a generalization of the idea of monoids, and he says that because we're playing with monoids, these things should be generalized to this concept of monads, and it's coming from that particular example, but also that later on, he's going to talk about polyads. And don't ask me about what polyad is, because I don't know what a polyad is. And so that's where the term monads comes from. Okay. So let's think about where we've arrived. So we've got monads, but I haven't really told you about category theory in computer science. And so I spent a few weeks digging around there as well, just to get a sense of where it came from. So we've got the introduction of category theory, and I didn't go into the beginnings of that in this talk, but I was tempted to. So the categorical semantics of computer science really come in quite clearly in the work at IBM. It's possible that there were things before this as well. It's actually quite difficult to separate computer science from mathematics when you start thinking about things like automata, automata theory. And that's where a lot of these things started out. But some very early work is by these people. So Eilenberg and Wright start talking about automata theory or generalized automata theory and algebra. And they're thinking about universal algebra. So universal algebra is the study of essentially operations with equations. Sounding familiar? And operations with equations are, at the time they know, are Levert theories, and they just want to study how these things work together. And some of these things say something like, the basic language for these are categories, and we're working with Levert theories for the obvious reasons. So this is already in the sort of DNA of computer science from some very, very early on, so it's like 67. What I find interesting is this little clip from the paper which says, oh, it's clear from this introduction that this paper contains nothing that is essentially new, except perhaps for a point of view. So when I write papers that have some category theory in it and the reviewers say, there's nothing new in this paper, the point is the point of view that's the new contribution to these things, and that has been all along for a lot of these important papers. So sometimes just seeing a piece of research from a new perspective sheds enough light on something to make it clearer, and I think that's a very valuable contribution. So that's what they were saying right from the beginning. And actually, a lot of these ideas get crystallized and worked on by this chap called Elgert. And so he's thinking again about automata and how that relates to category theory. He, from his first paper, is thinking about Levert theories. And then in 73, he talks about monadic computation and iterative algebraic theories. He's thinking about algebraic theories from the beginning. And I think what's fascinating is that it feels to me as a researcher in functional programming, when I started doing research in functional programming, that all the category theory had kind of like been evolving towards monads for a long time, or that somehow it was a novel invention. It turns out it's not been a novel invention. It's practically the first application of category theory in computer science was monads. But I think it's so hidden away in history that we've kind of forgotten these facts, and I think that's fascinating. So what he does in this paper is he connects Levert theories and monads to study Turing machines. So amazing connections going on right from the beginning. Okay, where else do we go with this? So Matt Lane has his hand in this too. So he knows about the work of Elgert and people working in IBM on category theory. And at the time, he influences the young Goguen and says, you should go there and work on some problems because IBM are interested in categorical semantics. So Joe Goguen was apparently in a lecture series of Mac Lane's at the time when he sort of was told that this would be a good research direction for him to go into. So when he gets to IBM, he teams up with Thatcher, Wagner, and Wright. Elgert was there as well, but I can't find any papers written by all of them together. And they form this group that they call the ADJ group. ADJ because they're the first letters of adjunction, which is an important categorical concept. And they write this paper called a junction between computer science and category theory as a big pun. And their idea really is to write a series of papers which will be a complete retelling of the way we do computer science, very much a la Nicolas Bourbaki. So Bourbaki was a a fictitious character that mathematicians had invented sometime before in the study of, I think, algebra. Is that correct? Basically, it was a bunch of French mathematicians who got together and said they wanted to rewrite mathematics from a unified perspective. And they didn't want to write these papers with all the collection of all these people. So they invented this man called Nicolas Bourbaki, and he was the person that wrote all of these papers. And these guys are doing the same thing, but the group is called ADJ. And so they're very clear that the four of them, the author order is not in that order. It is a set that we should be considering here instead. And then for various reasons, it turns out that they were forced to write their names, and so this is how it worked out. Where do we go from here? They intended to write a whole series of posts towards category theory and how it relates to computer science, but they never made it past the first two parts of this. And this is like part 1 and part 2 of volume 1 of an entire thing that they had in mind, and then it just stopped. Classic. So in 77, they have a paper about initial algebra semantics from the perspective of category theory. So the idea here is that we have abstract syntax, and we want to give a semantics to abstract syntax, and of course the right way to do that is to think about what we call initial algebras, so this is free structures, and then what we have are being called homomorphisms from free structures are the way we should interpret these things. In other words, you provide me with an algebra, and I'll provide you with an interpretation of things. In other words, this is like starting with a list and folding over that list with a given f and k to give you the final result, except it's all generalized. So those ideas come in around 76 or so. And Birstall and Thatcher talk about this paper as well, which is where they start using monads to explain stateful programming. So in this paper in 75, they said they're going to be using some monoidal things or monadic things, and they have this little diagram where the semicolon is exactly sequential composition of sequential programs. So monads appearing in 75, at least in that setting. And that's not the history that most people will tell you when they ask where did monads come from in the functional programming community. They will normally tell you a slightly different story. And that story starts, I guess, with Dana Scott. Dana Scott was thinking about what would the theory of the lambda calculus look like. And that was in 1980. And what he surmised was that the theory of functions should be based on something, and it should be based on the theory of category theory. That's the right abstraction, he thinks, for thinking about functions in the first place. And so he says, what kind of theory should we be using? Everybody knows it's got to be category theory. And he wants a very sort of pure theory of this to be there. The idea is picked up by Eugenio Modi. Eugenio is thinking about the lambda calculus and how he's going to give a semantics to that. And he takes the view and uses monads. The monads should give a semantics of lambdas. And so he gives this paper where he basically says category theory should give the semantics of computations based on monads. And he also wants to give an understanding of concepts such as state and exceptions and how they should be modeled. And so he very explicitly starts talking about those two functors in that paper. Again, side effects with the statement and exceptions are sort of really the contribution that Modi has in the context of the lambda calculus. In 91, he extends that paper with a whole bunch of other examples for different notions of computation that we know and love today. So things like partiality, non-determinism, side effects, exceptions, and so on. So this is kind of a good treatise of the variety of things that are monadic, all in one paper. Okay, but that's not exactly how things arrived in functional programming. This is about lambda calculus. So what about monads for effects, and where does the history of that come into play? So the story for effects, as we would understand them today, really comes about from this gentleman, Philip Wadler, in 85. He's thinking about how it's possible to have something like exception handling built into a language without exception handling being primitive to that language. So he wants there to be some kind of mechanism that, from which exceptions are derived. And for him, he realizes that actually that's possible with lists and laziness. So if you have a lazy language with lists, you can also have exceptions. And so this is why we have the paper about what is it? How to replace failure with a list of successes. So he goes in and explains these concepts. But the term monad isn't appearing at all here. It's really just, here's a different mechanism for doing exceptions. His paper is picked up by Spivey. In 1988, he writes this paper, although it's not published for another 2 years. So Spivey notices that there's a connection between what Wadler is saying and category theory. So he notices that actually what you want for exceptions isn't lists, it's some other thing which he calls the maybe monad, and he introduces the terms just and nothing to correspond to the categorical notions that we have. So we're seeing back in 88, these are where these terms come from. And he uses return, join, and Kleisli composition, the fish in Haskell, in order to describe how monads should work together. So of course he doesn't call them return, join, and fish, he calls them succeed, prop, and question mark, question mark. But he's basically explaining how monads are fundamental to these different constructions in this paper. That's sort of monads for effects, but what about sort of sequencing things together? Well, that has a very related but slightly different history, starting in around something like 86 with the work of Richard Bird. Richard Bird is thinking about the theory of lists. So he likes programming with lists, and he likes people to reason about the programming with lists in a kind of calculational style. And because he's thinking about calculation, he also wants there to be a theory of, or a collection of laws that we should be using to manipulate those equations from the go. And so he introduces this paper in 86 and 87 where he comes up with a calculus for functions for program derivation. And in that calculus, he shows things like, so this funny f star is like the mapping function of some function f over a list, and he shows some various laws and properties about that. And he shows this property here, which says something like function composition and mapping should somehow be coherent with each other. And he gives the definition of what we would call the map function in that paper. But of course, remember, the mapping function isn't new. That was invented in Lisp right at the beginning of functional programming. But nevertheless, this is a theory of how that's all sort of compatible and useful for program calculation. I think that's the contribution that we have in the late 80s. And again, Mike Spivey looks at this work and says, hang on a minute. This is all to do with category theory. And he notices that everything that Bird has been doing is about natural transformations and functors and adjunctions and monads, which he explicitly says. And so in his future work, he says, well, clearly we want to be doing stuff with monads and all of this. Now, in that paper, he actually implements a variation of the free monad. Now, to give you context, if you don't know what the free monad is, it's basically just a monad for syntax. And it's the monad that's underlying what we would do in the effects and handlers story. So the effects and handlers story is all about starting with some syntax and then interpreting that syntax in some way with some semantic functions. And we see that happening in 89, already in Spivey's paper, where he defines this new data type called exp of alpha, which has a constructor var and apply var for variables in your syntax tree and apply for nodes of syntax in that tree. And he shows that there's a function which he calls subst for substitution, and that's basically saying if you have a term and if you have a function that tells you how to replace variables in that term with a new term, then you're able to just sort of apply that recursively. And that's what we would call now monadic bind. So the bind for the free monad corresponds exactly to the substitution function. So this, I think, is the first appearance of bind in the literature. But of course, it's not written greater, greater equals. Actually, does anybody know where greater, greater equals come from? Because I actually don't. And I've dug around a lot, and I've got no idea. Nobody knows. So I've asked him, and he doesn't know. I think it's Spivey in lecture notes that when he taught me functional programming, he uses a right triangle. But it's a filled-in right triangle, and so that's the earliest thing I can think of, and it kind of just creeps into the literature at some point, and nobody cares about it. So anyway, let's carry on. Monads in Haskell. So where do we get to with this? Phil Wadler was really instrumental to the way we use monads in Haskell today. What he did was in 1990 he started thinking about how we could use Spivey's ideas to write programs, but he doesn't like the way that Spivey's producing programs by sort of slightly difficult to manage functions all applying to each other in slightly tricky ways. What he wants is some clean notation to do this, and he introduces monad comprehensions, which are a controversial feature. I think they made their way into the Haskell report and back out of the Haskell report, only to be put back into the Haskell report something like a decade after. So the idea really is that he wants a cleaner notation to do these things. And in 92, he basically says, well, actually, monads are very useful for programming, and he gives a plethora of examples. So he talks about the standard interpreter, i.e. the identity monad, where basically function composition is what sequencing does for you. He has one about error messages, which is the maybe monad, but with a payload of data. Error messages with positions, which we might now call the reader monads combined with errors. The state monad, output, so this is going to be something like the writer monad. And he has non-deterministic choice, which is the list monad. And then he has this very odd one, propagating state backwards, which is completely bizarre. And he has a little note that says, this example may seem contrived, but this monad arises in practice. John Hughes and I discovered it by analyzing a text processing algorithm that passes information both from the left to right and right to left. To make this change in an impure language is left to the exercise as an exercise for masochistic readers. So I have no idea how they came to this example, but that's what they did way back. I'm sure John can tell us all about it later. Then we need to kind of think a little bit more about where monad transformers get to. So I'm kind of assuming, this being the Haskell Symposium, that people are fairly familiar with some of these concepts. But in case you're not, the idea with monads is that we have a way of sequencing programs together. But it's not necessarily the case that monads compose. In fact, from a categorical perspective, we know they don't compose very well at all. So what we end up having to do is transform monads from one monad to another by sort of equipping it with additional operations as you go. And so this is the story of how you start getting modularity into programs in that manner. So the story again starts with Wadler and Blott in '89 this time. And these chaps are thinking about type classes. So they want a kind of ad hoc polymorphism, but slightly less ad hoc than ad hoc. And so that's where type classes come from. The idea is, how can we make it so that we have specialized code for a particular context? And so type classes are born. They start with the example of nums and addition and multiplication with negate. And sort of they leave it there, as in the introduction of classes is for things of kind star. Mark Jones in '93 notices that that's a bit too restrictive. So he's thinking about how you might be able to use type classes for something like the map function or the fmap, the functor instances. And he notices that you can just about manage it with type classes as they existed at the time, but it's a horrible hack, and it doesn't really work very nicely, and it's not good to work with. So he thinks that what we really want are type classes to be also extended to constructor classes where you're able to take things of kind star to star as well. And so he introduces the first functor instance in that paper, which is exactly as we know it today. And then the monad instance, which is exactly as it should be, with just a functor constraint, but also with the introduction of bind and join as being the two primitives for combining things, both interdefinable in this way. He also introduces in that paper the idea of the state monad. So the issue here is that monads generally are not interesting. They're not interesting because all they tell you is that things can be put into sequence. They become interesting when you equip them with additional operations. And in this case, let's say, the operations of state. So if you can equip a monad with not just the fact that it's sequencing, but it's sequencing and you can update the state, now we're talking, and now we have interesting effects. So the state monad class is something that he introduces here to capture the idea of stateful monads in a more general setting. And it's fun to see that happening so early on, because quite a lot of beginner programmers, when they start playing with monads, work with a specific hard-coded state monad, and they work with the operations of that alone without thinking about the more general abstraction. But that's exactly what Jones does right at the beginning. So in that paper, it's '93, he also introduces the monad transformer, which I find astonishing that in the very first paper that talks about monads, he's also introducing monad transformers. So this is the idea that state M can take an arbitrary monad M and augment it with the abilities to do state. And so he introduces he shows that it's an instance of monad, he shows that it's an instance of the state monad, and carries on with that. There is a little wrinkle in his theory at the time, which is that the operations of the underlying monad that you're trying to augment with state operations, the operations of that underlying monad don't necessarily sort of get used in the current monad that you're working in. It's difficult to express those underlying operations in the current context. And so a couple of years later, in '95, we get the monad trans idea coming in, So the nuance here is that there's a new function called lift, which allows you to lift or reuse operations from somewhere further down in the stack into your current context. And that's the contribution of Liang, Hudak, and Jones. So this is really the basis of the MTL library that we sort of have today. And I think it's good to sort of just pause and take stock of where we've arrived. So MTL, I think, sort of ruled the Haskell effect scene for about a decade from this point, relatively untouched. So the slight wrinkle was, should we be using functional dependencies or should we be using type families, sort of came a little bit later. But for a very long time, this was the standard that everybody used. And it was a good standard because you could have different effects layering upon each other and you could reuse things from further down the stack. So perhaps we could have just stopped there and we don't need any more research to happen. But of course, something did happen. What happened next was effect handlers came. And so what's the story with these things? Effect handlers are a separation between syntax and semantics, harking back to the 1970s. So the idea is that syntax is represented by the free monad for a functor that provides a signature. So the idea is that you tell it what kinds of operations you want to have, and you say it's possible to build a tree, a syntax tree with those operations. And from the semantics perspective, we have a fold over that tree that tells you how to interpret the tree in a very structured way, harking back to the 70s, where you've got this denotational semantics game going on again. So why do people start getting excited about algebraic effect handlers? Well, there are all sorts of reasons. So we have a syntax program. So imagine this is the program that you have. It's got some OR nodes. It's expressing non-determinism. It's a syntax tree. The point is that programs are syntax. They can be inspected. You can look at them. You can program with them. But rather than just doing willy-nilly functions over this data type, you want there to be a structured recursion over this, just like folds. And so you can give them a denotational semantics by having a handler that knows how to deal with the different nodes in play. Furthermore, these nodes are all what we call algebraic. Now, when somebody says, oh, it's an algebraic effect, it sounds like a very mysterious thing, but all it means is that essentially bind distributes into all of the different parts of the program. So if we look here, we've got some program OR PQ, and if you extract x from OR PQ and you continue with x, that should be the same as, if this thing is going to come alive, yep, that should be the same as this thing here, which is saying you can either bind x from P and then continue with it, or you can bind x from Q and continue with that. So the continuation structure sort of passes into the parameters of the operation, in this case, the operation OR. So that's what it means to be algebraic. Now, the next thing that algebraic effect handlers give you is this idea of being extensible, in the sense that your syntax trees needn't be fixed in terms of the kinds of syntax that they can represent. So you could have non-determinism. You might want to also add failure to this, or state, or whatever other fancy things that you want. And so you can modify the tree to contain different syntactic constructs. They're also going to be modular, which is to say that you can decide to handle certain parts of the tree, leaving certain other parts of the tree unevaluated, and then later on, evaluate those other parts of the syntax tree that you haven't yet touched. And you can keep doing this in succession until the tree is all gone, and all you're left with is the semantic domain, i.e. the result that you were looking for. And what's useful about this is that we're starting to break into the modularity problem that monads were solving with MTL, but without the restrictions required of proving that the monad trans stack that you're building is correct. So when you're doing MTL-style monad transformers, you have a proof obligation that says that the lift functions really behave like you think they behave for all the different combinations of effects in play. The idea with algebraic effects is that that should come for free by the construction of the effect system itself, and that's sort of ensured by the algebraicity of the operations. So there's no proof obligation to be done here. It all comes automatically. That's kind of the insight that makes this useful. They're also flexible in a way that monad transformers aren't in the MTL. By this I mean, so on this previous slide, I've got the interpretation of OR using append. So you see it on the top part of this diagram here. There's a 3-second lag, which makes it hard to do this. So there's a plus here as being the interpretation of OR, but there might be other ways of interpreting OR as well. So perhaps what you want is this left angle plus right angle, which says that we're interpreting this into the maybe monad, which is going to be left biased so that justs prevail on the left and nothings annihilate things to the right. So giving multiple semantics to a piece of syntax is actually quite a useful feature. you don't get that MTL style because you're locked into the semantics by the type of the monad that you're dealing with, whereas in the effects, algebraic effects world, you can provide a function that determines how to interpret things as you go. This is a little bit akin to having, imagine if you had lists, and the only thing that you could ever do with a list was sum it, because the resulting type had to be an integer, and all you do is take the monoid instance of integers, which is, let's say, addition, and that's the only semantics that you get. But we all know that programming with lists isn't just about summing things together. We could do many more things with lists than that. How do we achieve that generality? Well, with fold right, taking in different parameters f and k. So we dynamically change the semantics that we assign to lists, maybe doing products, maybe doing lengths of things, by changing the functions that we give in. Similarly with algebraic effect handlers, we could lock in our semantics to a particular meaning, that's the MTL style, but rather we would want to change the meaning of the program as we go, very much like we did with lists, and we can do that by providing different algebras. So that's the kind of the philosophy behind this. Okay, they're also equational, by which I mean that you can add extra equations to your theory. So here I'm writing an equation that says all PQ is the same as all QP. In other words, this is a commutative semantics. Now, Haskell doesn't enforce that this is true, but behind the theory, this is something that you should be able to do. Another thing is that they're pervasive, by which I mean there are lots of different effects in play. So printing, getting, putting, throwing, forking, reading, and writing. It sounds like Daft Punk. Do with these kinds of things. And finally, they're efficient. So the theory tells us that there's a way of doing fusion over trees, and that plays well with all of this as well. So there are lots of reasons why people get excited about algebraic effect handlers. So to get back into the history of that, we talk about Bill Levere and Levere theories and where they came from. So he wrote his thesis in '65, which in another historical note, it turns out that his supervisor, Eilenberg, openly admits that he never actually read his thesis until years later and had no idea what was inside it. So it was left relatively untouched for a while. But many people took the ideas of Levere theories, as we saw earlier, realized that they were important. John Power, quite some time later, in '99, came up with the concept of enriched Levere theories. Now, there were many, many extensions of Levere theories. They were used extensively up until this point. But Power wanted to have a way of talking about Levere theories in the context of computer science. So prior to that, Levere theories were over the category set, and that's not quite powerful enough for the kinds of things that we do in CS. Levere enriched things to make that possible. He then worked with Plotkin to write a whole sort of semantics for what algebraic effects mean, and why they're good for computation, and lots of different effects are relevant there. And then they come up with this lovely paper in 2002 called Notions of Computation's Determined Monads. And the idea here is that they don't think that monads are the way of understanding effects. They're just a way of interpreting effects. So you can think of, so I think a kind of a crude way of understanding effects is an effect is a monad. That's not true. These people are saying an effect is operations with equations, and they determine a monad, which happens to be the thing that you're talking about, but it's the operations and the equations that you started with. They are the building blocks of effects, which then determine monads that you could then play with. So that's the conceptual difference that they have. The reason that this is all interesting here is because effects can be combined together in interesting ways. This is the work by Hyman, Plotkin, and Power in 2002 that shows that these things are very modular. And eventually in 2009, we get the work of Plotkin and Pretnar showing the distinction between operations and handlers of those operations. And the sort of the insight here is that operations correspond to ways of constructing effects, ways of constructing trees, and handlers correspond to ways of deconstructing effects, in other words, folding over things. So at this point, we're in around 2010, and I'm trying to summarize some history of where algebraic effects went from that point. And I must admit that I failed. Because here's the effects library, bibliography, which Jeremy Gallup compiled, where people get to contribute the kinds of things that they've been working on in algebraic effects. And if you look at this website, you will find pages and pages and pages and pages and pages and pages of papers. And so I struggled to kind of put this together into a coherent story. But the point I want to make here is that there's lots and lots of research going on in algebraic effects. It's very, very exciting. And although I could touch on all these different topics, I think it's unclear at this stage which ones are the best ideas or the most important ideas. And I'd rather let more than 10 years go by before we settle down and say, these were the biggest contributions, but there are many. What I'm going to do now in this talk is be less historical and much more opinionated and more about my stuff. So higher order effects and scoped effects are really where I stepped into this field. And let's talk about where the ideas for that came up with. And here's a funny story. So I'll take you back to ICFP 2018. We're in St. Louis at the Haskell Symposium, actually. So ICFP's just finished. And this chap, Rob Ricks, is sitting in the corridor hacking away, and I start talking to him. And he says, well, algebraics are really nice, but we can't express lots of constructs like if statements and try-catch as syntax, and that's really troublesome. He's working at GitHub, and they want to do code analysis, and they want to be able to have algebraic effects for every piece of syntax that you can imagine in every single language, so that they don't have to re-implement everything for every different language. So they want to have a kind of compositional way of putting things together. But it's not working. And the problem is that for some reason, if statements aren't behaving, try-catch statements aren't behaving. There's no sort of algebraic way of dealing with these things, and it's bothersome. And I start talking to him and say, it sounds like you're after something that I'd call scoped effects. So scoped effects are syntactic constructs where there's some piece of code inside your operation that you want to deal with before you think of it as being complete. So I showed him a whole bunch of papers that I'd been working on. So this story starts in 2014, a collaboration with Tom Shrivers, Bernard Dussoutier, and Dermoin. And we were thinking about how to do Prolog in Haskell. So we wanted functional logic programming. Fancy that, yeah. And so we wrote this paper called Heuristics Entwined with Handlers Combined. And the idea with this paper was that, well, if you have a non-deterministic computation, so here's the little OR tree that we had earlier on, as a Prolog developer, you might want to have multiple ways of interpreting this. So you might want to say, I want depth first search. Oh no, I want breadth first search. Oh, perhaps I want depth bound search, or I want just to get one result. These are different semantics that we might give to this tree. So given what we know, this is clearly an example of algebraic effects. We have a handler for this tree, or multiple handlers for this tree, depending on what you want to do with it. So we use this to model basically Prolog as a DSL within Haskell. It turns out that these different handlers, DFS, BFS, DBS, and once, they all have related behavior in the sense that, okay, sure, they do different things in terms of their traversal strategies, but they're combined in the sense that if you search for fail, you get fail. If you search for return X, you get return X. And if you search for search, you get back the search. So these are just some laws that correspond to how these different handlers might behave. So there's a kind of an equational theory that it relates all these different search strategies. But the trouble is that these search strategies are not algebraic. So the theory of algebraic effect handlers doesn't apply to things like DFS, BFS, DBS, and once, even though it feels like there's an equational theory that binds these things together. So they're not algebraic. Is there a way that we can somehow extend the idea was the connection that we had there? A little bit later on, so in the same year, we write this paper about effect handlers in scope. And the point that is that, as I said earlier, bind has to distribute nicely in algebraic operations. So this is what happens with fail, or, get, and put. But scoped operations don't behave in this nice way. So if you have catch ph followed by k, that's not the same as catch p followed by k, h followed by k. So let's try and understand this. Catch ph is saying, I'm going to catch errors in p and handle any errors with h. Once I'm done, I'm going to carry on with k. Okay, so that's what the thing on the left-hand side says. On the right-hand side, it says, I'm going to catch the program p followed by k, and if something goes wrong, I'm going to do h followed by k. And there's a subtle bug here, which is if an error is raised in k, on the right-hand program, it might get raised and raised again. And so that's not what we want. So it's not a correct semantics. Catch is not algebraic. The once example is not algebraic either. So once is the idea that you have a non-deterministic computation and you want to pluck out the first result from this computation. So once p bind k should run p, and maybe you get lots of answers, but you just pick out the leftmost one, and then you continue with that answer in k. And k might then fork off that answer into different subparts. But on the right-hand side, we have once p bind k, which says, okay, so p bind k would be you do p, you generate lots of results, and then you pick out one, which is the first one perhaps, and then you want to once that. That's not necessarily the same thing, because on the left-hand side, p might have generated one result, then k produced like 10 results, say, from that. So the resulting thing on the left-hand side is 10 different results, whereas on the right-hand side, p generates one thing, k turns that into 10 things, but then you once it, so you only have one thing again. So again, that's not equational, that's not algebraic, it doesn't work. So the insight here is that free monads are a little too restrictive. They don't allow you to have internal computations that do something different. And so we generalize the free monad, which is this thing, to something slightly different, which is the higher order free monad, which looks like this thing. Is that exactly the same? No, there's a single parenthesis difference between the two. So if you look really, really carefully, there's like down here you have a bracket, bracket, and over here you have bracket, a bracket. and apparently that makes all the difference. So the idea is that we're moving from a setting where signatures are given by functors of kind star to star to where signatures have kind star to star to star to star, where you go higher order. It turns out that gives you just enough power to fix this problem and work with it. So I showed Rob this paper, and he implemented it. He said, "Wow, it works, but is it efficient?" And the answer is yes. It does all fuse very nicely. So I showed him another paper and showed how fusion is completely compatible with this technique. And they went away and programmed something that was 250 times faster than other libraries that they worked with. And they were very happy. And they shipped it into GitHub Live. And in production, they had Haskell running, doing on every single pull request, every sort of push into GitHub, they were doing code analysis running this code, which was great. So people were very excited about this because it allowed people to do sort of code navigation features in GitHub's website. And we wrote something about that in 2022, just explaining some of the details around that, which you can have a look at. So that's the story of scoped effects. But of course, I'm skipping out a whole bunch of history. So this is the fused effects library that came out of that work, which was initially almost a transliteration of the work that was in the effect handlers and scope paper. Of course, there are lots of other different papers that were preceding this one that were, in some sense, more important, and that they also gave rise to lots and lots and lots and lots of different libraries. So there's an absolute forest of things. Oops, there's an absolute forest of, oh dear, of trees. There's a forest of libraries. This has all gone to pot. And it's very difficult for people to choose which one they actually want to be using. So this is the kind of mess that we're in now with regards to the effect system. And it's kind of healthy because it's really an indication that there's lots of work to be done and lots of engineering decisions to be made. But it's also not very healthy because beginners have no idea which one of these things to choose. So I would kind of encourage the community to perhaps slow down a little bit and think a little bit and maybe collaborate with each other a little bit to try and come up with a sensible way of doing algebraic effects. OK. I have tried to condense a lot of research into the past sort of hour or so. In fact, I've tried to condense the last 71,000 years of history into the last hour or so. And that's been no easy task. So, but the thing I want to just terminate on, the question of what next. Will there be one ring to rule them all? Is there going to be a kind of final algebraic effects handler library? I don't really know. We want this thing to be modular. We want it to be expressive. We want it to be convenient, and we want it to be efficient. All sorts of different design decisions. And this is giving rise to the various libraries that we're seeing today. So from my very opinionated perspective, the most important one of all of these is actually expressivity. I want my effects handler system to do lots of different things. We can work on efficiency later on. We can work on these aspects of convenience and easy syntax. And I think we can get around those problems. But expressivity is the real hard one to crack. And I think we've just about cracked it. Because of the scope problem, which has now been solved, that's sort of unlocked handlers to work in a much larger domain than before by having this tiny little augmentation from the free monad to the higher order free monad. Actually, later work showed that we could have various variations of this monad in play, whether or not you wanted to tell the user if you're doing something that's algebraic or scoped or whatnot. Later on, we did some more work showing that latent effects, where you have some ambient effect stuff hanging around, is also important. I won't go into the details. But is there one ring to rule them all? And actually, very recently, Tom Shriver and Bith Vandenberg have written a paper that's just been accepted about a framework for higher order effects and handlers, where they go for free H as being the way of doing things. And this is actually implied by the original thing we had in the handlers and scope paper, but with a slightly different interface. Actually, just this week, Zhixin Yang presented a paper about modular models of monoids with operations, the MoMoMo paper, which from the theory perspective confirms that this is exactly the implementation that we want. So I think that we are just about turning the corner in terms of understanding what we want from algebraic effects. But we're going to need quite some more time in order to make this a convenient and efficient library. So I have some code that works that is very expressive. And I'd love to release that to you all soon so that you can all hack on it and make it efficient and better, et cetera, et cetera. But it's not quite ready yet, so hold on to your horses. And with that, it's the end of my talk. Thank you very much.
Yes, thank you, Nick. That was a very nice talk. And I'm here to ask questions.
Hi, Sven Keidel, TU Darmstadt. So I've never used effect handlers before. So which of these libraries should I use?
I tried to stay away from answering that question. I personally like the fused effects library. I think it's a very good place. But it really depends on what you want. Are you after, expressivity, or are you after efficiency? Like it's just difficult. I think I would point you to the fused effects as a starter point, but it's not necessarily the best for everything that you might want. And I say that with bias. So I'd say it's very hard for me to answer that question today. Yeah.
Thank you. You've pointed to libraries. Oh, by the way, that was amazing.
Thank you.
You are the new Phil Wadler of the history of computer science. You must have done an awful lot of homework.
Yes.
Scary. In French. You'd enjoy Stephen Wolfram's writings as well. He's written a whole book like on combinators as well. It reminds me a lot. My question is to do with, you described various libraries, right?
Yes.
But a language like Coca has effects as a sort of, built into the language syntax. And so how far can we get with libraries, and do we need anything built in beyond, some primitives to make it more efficient, which Alexis has done more recently?
That's a great question. I think the work of Alexis is fantastic in terms of making things more efficient. There were other ways of solving that problem, but that's a good one. Mm-hmm. I think there are two things that I would like to have. One is sort of you can get around it, which is algebras are a little bit of a pain to express in Haskell at the moment. Now, we can do them with just functions in the style of lists with the function f and the k parameter that sort of deal with things recursively. If you look at effect libraries, they have slightly more convenient notation to say, hey, look out for one of these things and do this with that. And you can kind of simulate that in Haskell using view patterns and projections and all the rest of it. But it feels a little bit kludgy and a little bit painful, and I think there are problems around error messages and sort of making this a more inbuilt first-class part. And I think we can probably engineer our way through most of that, but having that built into the language might be a good thing. The second thing that I think is really missing is actually something like row types in Haskell would be fantastic. A lot of what's going on with these effects is that you want to be able to pick out different effects and say, I'm going to deal with this, and I'm going to deal with that, and then I'm going to add this effect, and I'm going to take this one away, which is exactly what row types is good for. And a lot of these libraries kind of simulate row types, and we simulated row types using the data types a la carte methodology. But there are other ways of doing that, and the more modern ways of doing that using things like heterogeneous lists and pulling out different parts. But these, I think, are all sort of very engineering hacks around the problem that Haskell doesn't have row types.
Because we don't have the thing.
We just don't have the
We just encode the thing.
So give us row types, and things like this would just be a lot less painful. I think that would be, so those are the two, I think, big hurdles towards making this more first class.
Thank you. I didn't understand all of that answer, but I think a blog post expanding on that would really be quite helpful because you're well positioned to.
There's one last thing I want to answer that, which is actually unsaturated types, I think, would be a really good thing to have. So I know that the paper is...
unsaturated type families.
Unsaturated type families would be very useful for making the kind of extracting values out of computations without having to unwrap lots of different new type constructors. I think that would be useful too. But again, that's not been implemented yet. So
we have a paper.
Yep. Yep.
Norman Ramsey, Tufts University. I want to sort of ask a question very similar to the first question. As a humble compiler writer, I was initiated into the world of monads really by two papers, both of which you mentioned. Phil's paper on, I'm blanking on the title, the 1992 invited talk at Popple.
Yes.
With all the interpreters. And then the monad transformers and modular interpreters by Lang and Hughes.
Yep.
Can you recommend one or two papers, just at most two, for someone who's really brand new to this to get immigrated into the world of algebraic effects?
I saw Sam Lindley just shaking his head. I could give the opinionated. I think that the handlers in scope paper I wrote is not too awful. There's a paper that I wrote with Tom Shriver's Maria Skalioff and Maciej Pirog, which compares monad transformers and effect handlers in terms of expressivity and what you can do with them. So if you already know MTL and you want to think, how would I use algebraic effects in that style, that's a pretty good place to look as well. So it's a good kind of bridge between the two. And I think early on when people were doing algebraic effects, there was a lot of hype and a lot of misunderstanding about what they could do. People were saying algebraic effects are strictly better than monads. That's not true. And that paper is about showing actually monad transformers are every bit as good as these, and it's just the convenience of certain features that you're looking for. So that paper, I think, for someone like you who probably knows MTL very well, look at that paper. So that's monad transformers and algebraic and modular algebraic effects as a good starting point.
All right, thank you.
Yeah.
Very tall in this room. Thank you. Hey, so you did a lot of research, and so something I noticed when I first learned about algebraic effect through the Pretnar and Power papers is they talked about Liouville theory a lot, but they don't feature any Liouville theory.
Yep.
They feature presentations of algebraic theory
Yes.
with operations and equations, like you talked about,
Yep.
which is much older than Liouville himself.
Yes.
Right? Have you managed to figure out, like you mentioned Power's thought about Liouville theory somewhere along the way. Did you manage to trace the idea from Liouville theory to that? Like, was there a research path that made that happen?
So from Liouville theories to sort of Power's observation, Plotkin Power's.
Well, I mean, they speak about it. Probably there was an inspiration
Yeah.
for that, and
Yeah. So I think it does start with the work by Power on enriched theories. I think he really was thinking about how you can deal with operations in the Liouville theory style with theories proper. And I don't think any of that really got forgotten in the work of Plotkin and Power. I think they were always about equational theories, as was the work with Pretnar and Plotkin on algebraic effect handlers. I think it's more an implementation issue that we don't have a good a way of dealing with equations. Although we've got a paper that's under review that deals with that using cubical agda for the equations and quotienting and all the rest of it, and that's kind of but I think it's more the implementation hasn't quite caught up with the theory, is probably how I would say that. Does that answer your question?
not fully.
Okay.
But maybe it's something we should take with pen and paper outside if you want to go. But
Of course.
The general point is a presentation, like Liouville theory are presentationless, right?
Yes.
And everything in the papers, it's not about equation or anything, they're presentations.
Yes.
And it's important because you want to list your primitive operations.
Yes.
So it's a very different point of view than Liouville theories.
Yep.
But somewhere there, they are the inspiration. And
Yeah, I think it's there in the early work of Power, but let's talk about it more later. Yeah.
Sure.
Yeah.
Questions? So I have one. So you said you are going to release a unified framework for effects?
So yes, I think that the answer of should we do scoped effects or latent effects or all these different variations, which are generalizations of algebraic effects, that's lacking a good implementation. And I've got on my laptop right here an implementation that I think works really very nicely. It's good from the expressivity perspective. It's not at all optimized or efficient or all the rest of it. And there are much clever hackers like Sandy Maguire or Alexis King who are going to, or Roberts who will be able to take that and make it much, much better. But from the expressivity perspective, I think it's the state of the art. Yeah.
Good. Okay, thank you very much. That was very nice.
1, 2, 3. Yeah. Shall we get started? Okay, welcome everybody to the first session of Contributed Talks for the Haskell Symposium. As always, these talks are all live streamed. If you have any questions, especially for the online audience, please submit them on Discord, not the YouTube channel comments. And yeah, Minut's going to talk to us about effect handlers for programmable inference. So please take it away.
Thank you. Hi. Hear me okay?
Yep.
Right. Okay, so today I'm going to talk about using Haskell to improve probabilistic programming languages. Or in other words, I'm going to use Haskell to trick you into learning statistics. Okay, so what is a probabilistic programming language? So there are tools for inferring missing data. So there are two main steps to using one of these. First, the programmer writes a model which expresses a problem in terms of random variables. Then use an inference algorithm to learn the relationships between these variables. So let's take the following problem. Given some input x, we can see this generates a data point y according to a noisy line mx plus c. So I'll use the normal distribution to express this noise. Because we can observe what values of y are, this is known as an observable variable. We also have our suspicion about how the slope and intercept are distributed. But because these aren't tangible values that we can see, these are latent variables. Okay, so what I've effectively done is model our problem in terms of the variables we know about and those we wish to learn. If you were to write this as a program, let's say in Anglican, it looked like this. So there are two key operations that we need. The sample operations describe how we think M and C are distributed. The observe operation then says, given some random samples of M and C, what's the likelihood of them having generated Y? Now, an important detail to note is that sample and observe don't actually do anything yet. And that's because in probabilistic programming, we want to separate the model from the inference algorithm. So the model is just syntax. It describes a problem we want to learn. By later providing semantics to sample and observe, we can implement different algorithms that learn M and C. So how is this done in practice? Well, in Anglican, models are first compiled into continuation passing style. The user is then given a library of algorithms that can execute the model by interpreting sample and observe. Now, while this framework is very straightforward to use, what if you wanted to build your own algorithm? Well, this is difficult. The model is now in a very low-level representation, and each algorithm comes packaged as this black box procedure. So one alternative is a language called Gen. So here, you're given an interface of methods for interacting with the model. By then combining these in different ways, you can then implement your own algorithm as a regular function. Which is great because functions are super modular. However, the interface itself is fixed. So this means you can't program how the model executes, which in turn limits how you can program inference. So let's instead consider Pyro then. Here, algorithms are coroutines that you can program yourself. But like the other languages, the approach still isn't typed. So this means there's nothing restricting what sample and observe should do, and nothing telling us what information they pass. So it's easy to have one bad coroutine corrupt the entire algorithm. So these 3 points I've listed are all different but important aspects of inference programming. That is our ability to customize existing algorithms and build new ones out of smaller parts. However, most languages for inference are often limited in at least one aspect. So in this talk, I'm going to use Haskell and algebraic effects as a way of proposing a new approach to inference programming. Okay, so last year in ICFP, we developed a language in Haskell for modeling based on algebraic effects. And in this, you can write linear regression like this. So sample takes a distribution D that generates values of type A, and it gives us a sample from it. Observe is similar, except it also takes an observed value to condition against. So as this is the minimal interface you would need to write a model, you can think of them as having the following types. That is, they are programs that can perform observing and sampling side effects, as well as I/O. And this type prog is where the algebraic effects comes in, and it's how we capture models as syntax. So to demonstrate, if we were to desugar this model, we'd get the following tree. So the nodes of the tree are the op constructors, which have 2 arguments. The first is a specific operation belonging to one of the program's effects. The second argument is a continuation. it takes the operations result, and it gives us the rest of the tree. And finally, the leaves of a tree are the val constructors containing the output of our program. Okay, so using algebraic effects, we've captured these models as trees. We can then assign semantics to our trees by using effect handlers. So given a program that has E as its first effect, a handler interprets all the operations of type E, giving us back a program where that effect has been removed. So by handling all the effects in our program, we can fully execute it. So for instance, let's just define a handler for sample that just draws random samples. So if we pattern match on sample, we'll get a random value R between 0 and 1. And then by passing it to draw, we deterministically draw a sample from that distribution. In the last line, we'll then apply the continuation K to the result, which gives us the rest of the program which we recursively handle. Likewise, in the val case, we've reached the end of the program, and so we return the result. And then likewise, we can define a handler for observe. So here, I'm just going to compute the log probability of each observation and return the sum of these at the end. If we then compose these two handlers, we implement a very simple algorithm called likelihood weighting. So if I were to run this on linear regression at the top, we'd get back a list of weighted samples for M and C, where the values for M equals 3 and C equals 0 have a higher weight, which are the actual values I use to generate the data. Okay, so using algebraic effects, I've given you the following framework. The model is a program that contains abstract operations, sample and observe. The inference algorithm then handles these operations, executing the model thousands of times and generating some values that we care about. Now, while this was fine for the likelihood weighting algorithm I just showed you, practical real-world algorithms are much more complex with lots of moving parts. So these algorithms not only provide a semantics for the model, but they come with their own procedures and side effects that happen outside of the model. And this framework simply isn't modular enough to capture these details nicely. So we need a more fine-grained way of programming inference, something that consolidates what the algorithms have in common and lets us derive new variants easily. Well, the key insight of this talk is that we can do this by viewing inference in the exact same way that we viewed models. In particular, we can think of certain families or patterns of inference also as programs with their own abstract operations. By making them abstract, it can actually be clearer what an algorithm is trying to do. So for instance, one pattern of inference is Metropolis Hastings, whose key operations are proposing new samples and deciding whether to accept these proposals. Another family of algorithms are particle filters, whose key operation is resampling. To then derive a concrete algorithm from the framework, as the programmer, you need to provide two things. You need to give a semantics for the model operations, like usual, but also a semantics for the inference operations. So to show you how to use this framework, let me first explain what an inference pattern looks like. So we'll start off with Metropolis Hastings. So Metropolis Hastings begins with this tuple here, which you can think of as the configuration of the model. The important part is tau of type trace. So this is the sample trace of a model, and it lets us provide values for each random choice it makes. So by giving a model a large enough trace, you can execute it deterministically. The W is then a weight, and it measures how likely a model execution is to produce our observations. And finally, the X is the output. So in linear regression, this was the M and C that we were trying to learn. We then begin the algorithm by applying MH step. So the idea is that we're going to propose new configurations and decide whether to accept them by comparing with the most recent one. And over time, we'll build up a chain of these. So each step begins by getting the most recent one. Then we'll call propose. This takes our old sample trace and it generates a new one for us to try out. Exec is then a model interpreter. It executes our model under a given trace and it returns us a resulting configuration. And then finally, we'll call accept, which compares our new configuration with a previous one. If our new one is better by some unspecified means, then we'll add it to our chain. If it's poorer, let's say in the next step, then we'll stick with our old configuration. And then by recursing, this procedure continues, building up this chain of configurations. Okay, so I've described to you Metropolis Hastings as this abstract program. To derive an algorithm from it, you need to provide two things. You give a semantics for the model interpreter and a semantics for the inference operations. So for instance, let's derive an algorithm called independence metropolis. So we'll begin with the model semantics. To handle observe, we're going to use the likelihood handler from before just to sum over the log probabilities of the model. For sample, we're going to define a new handler that will execute our model under a trace. So a detail I didn't mention is that each sample comes with a unique address alpha. If our trace contains a value for alpha, then we'll reuse it to draw the same sample. And otherwise, we'll get a new random sample out and store it in our trace. Next, we'll define the semantics for the inference operations. So when we propose, we're going to do something very simple and just map random values across our entire trace. When we accept, we'll compute the likelihood ratio between the new and previous weights. If this is greater than some random point between 0 and 1, then great, this is good enough, and so we'll accept it. Finally, if we then slot in both of these handlers to our inference pattern, we fully implement independence metropolis. So if I were to run this on linear regression, we get back the following graphs. And this shows that we prefer to accept samples around m equals 3 and c equals 0, which is great because these were the values we were expecting. But if you notice, we aren't actually accepting many new samples. And this is because when we propose, we're effectively generating an entirely new trace. And so the chance of this trace being accepted depends on all of our new samples being collectively better than our old ones. One solution to this is single site metropolis, which you can derive in the exact same way just by swapping around some parts. So here, I've just changed the type of our weights, how we execute the model, and how we propose and accept. So the key difference is in how we propose. So here, I'm only going to generate one new sample R for some random address alpha, and we'll keep the rest of the trace exactly the same. So the chance of this being accepted then comes down to this one sample being better than our previous one. So if I instead run this on linear regression, on the right-hand side, you can now see that we accept far more samples for C especially. Okay, so I've shown you how you can derive two concrete algorithms from the same abstract program for Metropolis Hastings. Well, the same idea holds for particle filters, which you can also think of as programs with abstract operations. So let's have a look at how this works. It's a bit more interesting than Metropolis Hastings. So a particle filter begins with a model and a weight, which we then create multiple clones of. Each of these clones is called a particle. We then begin the algorithm by applying PF step. So the idea here is that we're going to step through each particle's execution in parallel. So we do this by first mapping step over our particles. So step is a model interpreter. It takes a particle and its weight, and it executes it, but only up to the next observe operation. It then returns us a suspended particle and an updated weight. Next, we'll check if all of our particles have finished executing. If they have, then great, we can return their results. Otherwise, we'll call resample on them. So the goal of resampling is to filter out particles that are less likely. So for instance, resampling might produce this, where lower weighted particles are discarded entirely and higher weighted particles are cloned. Finally, by recursing, this procedure of stepping and resampling continues. And at the end, we should get back a bunch of particles that are likely to produce our observations. Okay, so I've described to you a particle filter as an abstract program. To derive an algorithm from it, you follow the usual steps. You give a semantics for the model interpreter and a semantics for the inference operations. So one simple algorithm is called a multinomial particle filter. So we'll begin with the model semantics. For sample, we'll just have our particles draw a new random sample each time. Observe is more interesting because now we want to suspend our particles at the next observation. Well, this is easy using algebraic effects because we can access the continuation k. So when we match on observe, we'll now use k to return the rest of the program. However, this time, we're going to return it as a value and we're not going to handle it. This hence represents the suspended particle. Next, we'll define the semantics for resampling. So given a list of particles and their weights, we'll first make a discrete distribution over the positive integers. The numbers that we get back are the positions of the particles we'll continue executing. We can then extract these particles and pair them with the average weight. And then finally, by slotting both of these handlers to our inference pattern, we fully implement the multinomial particle filter. So if I were to run this, say, using 100 particles on linear regression, we'd get back 100 samples of M and C. So something weird is happening here. It's not that our samples of M and C are bad, but they're all the same. And this is happening when we're resampling. So in particular, when one particle has a far higher weight than the others, we can end up cloning that same particle over and over again, which limits the results we get back from inference. The last algorithm I'm going to talk about tries to improve on this exact problem, and it's called resample move particle filter. The idea is that after resampling, we're going to apply Metropolis Hastings to each particle. This is going to propose new sample traces for them and effectively move around the samples that they've already drawn. So we can derive this algorithm in the exact same way I've shown you already. So to support Metropolis Hastings, will now execute each particle under a trace. The interesting bit is how we resample. So here, I'm going to keep track of an integer t, which counts how many observations we've seen so far. We'll begin by resampling, exactly like the previous algorithm, except this time, we're resampling the particles' traces rather than the particles themselves. Then I'll use something called suspend after. This takes the original model and it returns us a new version that suspends at observation t. So the reason I'm doing this will become clear in the next step, where we'll use it to apply Metropolis Hastings to each resampled trace. The result we get back is a partial trace containing new samples up to point t and a particle that resumes from that point. And this fully gives us the resample move particle filter. So if I instead run this on linear regression, on the right-hand side, you can see that the particles we get back are really rich in terms of their results now. Okay, so to recap, I've shown you a new approach to enabling programmable inference. I've used abstract operations to reveal how the algorithms are structured, and I've used effect handlers as a way of programming them. So if you recall, there were three things that I thought were quite important for inference programming. The first was being able to reinterpret how models execute. So there are many ways of going about this. Some let you program your own execution, some give you a selection to choose from, and some can't be programmed at all. The second thing we cared about was being able to build new algorithms out of reusable parts. The most obvious way to go about this is to use functions. And while functions are super modular, modularity isn't the only thing we care about. For inference to be easy to program, it can be useful to have stronger abstractions, ones that make it clear how the algorithms are structured and how they can be extended. The last thing we cared about were types. This is the wrong room to preach about why types are important, but I think this becomes especially emphasized for designing inference, where we need to manage all of the messy side effects and imperative baggage that the algorithms come with. Typed functional languages like Haskell give us a really solid foundation for all of these aspects. And this was shown by a really cool language called Monad Bayes, which used a monad transformer approach for going about this. However, Haskell and probabilistic inference are individually quite hard, and intersecting them can have a really steep learning curve, especially when we start involving monad transformers. In this talk, I wanted to explore how effect handlers can provide perhaps a more intuitive or at least a more explicit interface for the average programmer, which still builds on the ideas of composition and type safety that we really care about. Thank you so much for your time.
Thank you very much. We have time for maybe one, maybe two questions, so please.
Hi, Alexei Radl from Google. Great talk. I've messed with this in the past, so separating models from inference algorithms is very dear to my heart. Can this framework implement a Gibbs sampler?
Implement?
A Gibbs sampler.
Oh.
The essential feature is that the proposal depends on the continuation of the model to propose from the local posterior.
So I think a Gibbs network, that would require a static representation of a model, as in you would need to know the entire model statically. So I've tried very hard, and I haven't managed to do so. And I think that's the end of my answer to that. So I'm not sure is my honest answer.
Any other questions? If not, then let's thank the speaker one more time. Thank you very much. Want to take your laptop?
Oh, yeah. This is mine. Okay. I might have misunderstood you. Yeah.
Okay, so our next speaker is Ivan Perez, who is going to talk to us about the essence of reactivity. Please take it away.
Oh, excuse me. All right. Thanks, everyone. Sorry for that delay. Thank you for sticking around. And yeah, I'm going to tell you a story about reactivity. And just if you have done anything with reactive languages, stream languages, time variance, user interfaces, animation, you probably have used one of those. You probably fell somewhere in one of those circles. Don't take the boundaries between those two literally. This is, I just drew it, by mouse, not by hand. But the thing is, it's a pretty complicated picture. It's really hard to know what's going on there, right? And even the terms that you see there have been used and abused to the point that we don't know what they mean anymore. And I can tell you from my experience working using temporal logic, for example, at NASA, is we have meetings where we have 1 hour discussions about a property in temporal logic, and we can't agree on how it behaves. And the gist of the problem is that we can't agree on what logic we're using, because depending on the reference that you use, the logic is defined in a different way. So it's a pretty complex thing to figure out. So just to make things a bit more concrete, this is an example of what functional reactive programming looks like. And there are different implementations, there are different flavors, but in functional reactive programming, the first-class citizens, or the things that you define, are called signals or behaviors, which are time-variant entities. And in the original description, they vary over continuous time. These days, well, it's to be discussed. But for example, the mouse position is something that changes over time, that varies over time. And you can see the mouse position as a position that depends on the time. So if you, So for example, if you define conceptually a signal carrying values of type A as a function from time to A, then the mouse position would be just a function from type to positions. So at any point in time, you know the position of the mouse. And you could define an animation as a signal that produces pictures. And you take the mouse position, you displace it by a certain amount, and then you paint a red circle on that position, and so on. Stream programming, it's kind of similar, but not exactly the same. So you'll see some similarities, but time is no longer continuous. It is discrete. Conceptually, you work with a co-inductive stream. And then, for example, in Copilot, which is the language that we have at NASA, an external stream, an input to the system, is defined as something called an extern, and it has this type. And in this case, we don't have tuples. We can't work with tuples, but we can work with arrays of fixed length. And then you can prepend samples to it. You can add a value at all times, so you have like point-wise modifications. You can project values from the array. So this, for example, would take the input defined here, which at any point in time carries an array with 2 elements, and it would obtain the first. So this would give you the x, presumably the x coordinate of the mouse position. And then you can apply point-wise modifications. So you see that you have temporal modifications here. You have point-wise or atemporal modifications here. How do these differ? Oh, what happened? Oh, boy. What's going on? Yeah. Is that you or me?
I think it's the last if you wiggle the cable back there.
I'm trying not to. Okay, let me see if I can not touch the screen. There we go. All right, we're back on. So how do these differ? Like, what are the different dimensions across which they differ? So you could consider that, and this applies also for the others that we saw in the picture. In some time, is continuous. In other, it's discrete. It can be bounded. It can be unbounded. It can be linear or branching. In some temporal logics, you have branching time. It can be explicit or implicit. In streams, time is implicit. There's a notion of passage of time in the fact that you enroll the stream in the different samples, but you don't know the actual time. If you want to know it, you have to count it manually. In others, in FRP, it tends to be explicit. Systems can be causal or non-causal. There are some FRP flavors in which you can describe non-causal behaviors. And then in some of them, you can work with any values that you can express in the programming language. In others, you have a restricted set of values, and there's good reasons for that. And then there are other constraints that you have to work with. Some of those flavors, there are constraints that have to do with memory consumption because of the target application. And we're trying to make sense of that picture. So for these two that we saw in FRP, time is continuous conceptually. It's unbounded. It starts at time 0, and it's explicit. And in stream programming, it's discrete, unbounded, starts at 0, and it's implicit. In both of them, you can delay things, but in one of them, you can delay with no limit. In Yampa, you can go as far back in time as you want. And for example, in Copilot in particular, this does not apply to all stream languages, but in Copilot in particular, you can only go so far back in time. And that has to be determined statically because there's memory implications, and it's used in hard real time, and it's used in devices with limited memory. So we need to know the boundaries. In some, you can look into the future. In Copilot, you can go back in time, and then you are allowed to look into the future, whereas in Yampa, for example, you can never do that. And in Yampa, you can put any value in a signal. And in Copilot, you have limited values, right? So these are how some of these differ. So going back to this picture, imagine trying to map all of that for all the flavors that you see around. If you're struggling to understand what it looks like, you're not alone. Right? It's really complicated, even for experts, even for people who work in this domain. We struggle to understand the difference between FRP implementations. So I've been on this race to try to minimize the number of implementations around, try to give people mechanisms to to define their implementations on top of more abstract layers so that it's easier also to compare them. And this is a bit what this story is about. This story is incomplete. You can be part of it. If you disagree, say it. If you think, I wouldn't do it that way, say it. If something's missing and it doesn't fit your use case, I want to know about it. We're only at the beginning. We're trying to figure things out. But the reason why we're doing this is because, first of all, we want to know how these frameworks compare. And specifically, we want to know if we see an expression in one of them, can we literally just translate it to another? And is it going to mean something roughly equivalent? Or does the meaning change completely? How does that affect the expression? And also, we have libraries of reactive definitions and so on that we would like to reuse for other frameworks. And we don't know if we can, because we don't know how the meaning maps across. So the solution that we opted for, at least for this paper, is this. We want to provide abstractions, both mathematical and programming abstractions, so that you can define a reactive flavor in terms of these abstractions. So you both tell the formal aspect of it and also the programming aspect of it. And in this talk, I'm going to talk about the programming only. And if you want to look at how those programming abstractions are defined mathematically, you can look at the paper. But to give you an example, a bit more concrete is, okay, well, you have reactive entities. And we said that we cannot put any values, so we define a class so that you can talk about reactive entities and their values in the present. So in the present, you can put values inside. This is, oh, yeah, okay. So you can put values inside, and you can apply a constraint to them. And that allows you to define if any value will be allowed or only some of them. And also, you can determine which functions can be applied to those values. And that gives you the versatility of saying not all Haskell functions can be applied, or maybe I have a specific type that represents functions in my language. And then what you see here is some sort of constrained applicative. Right? We have pure and apply, but they use these constraints and this fun instead of any Haskell function. Right? But the ideas are kind of the same. And this is the implementation for Yampa. The signal functions in Yampa are applicatives. So that's it. The story is settled. Like you just use pure and apply, and then there's use any Haskell function as the function type, and there are no constraints, and you were done. And this is generally true for, I believe, any applicative. In Copilot, the story is a lot more complicated. And I'll go back to this later, but I don't expect everyone to get this immediately or for you to remember these details. But there are two things that I want to highlight. The first one is that we do have a type constraint because Copilot is a language that is compiled to hard real-time C. So we only support the types that we know how to represent in C. And that is captured with a class called typed in the language. And that's why we have this here. And the other is that it doesn't support any function in C. Again, we don't have malloc loops or recursion, so we only support a limited set of functions. And we had to define, to give this instance in this abstraction, we had to define kind of like a wrapper for the Copilot operations. And that allows us to define the apply the definition of apply for the instance. Now that we have this, we can write a definition like that. Say something that is always true is just pure true. And what we know about the signature is that bool has to meet the type constraints of your reactive entities. And that's it. Now, what does this mean? If you're in continuous time, this means this is continuously true. If you're in streams, this means it's true at every sample. But the meaning is determined by, I hope I'm not pointing the laser at anybody over there. The meaning is determined by the instance that you pick. So you can start writing components this way, in a generic way, and then just determine how they're going to be interpreted depending on your use case. Now, those are point-wise transformations. meaning they are atemporal. You only look at the values now. You can put a value constantly, and then when you apply operations, they apply at every point in time. But the power of these languages comes from their temporal nature. So the first thing that we did in this interface is that we expect everyone to define the notion of time. Even if it is implicit, we need to know what the time is, because there's going to be operations that will still need to use the time. So we just define a class with a type for the time. And in the case of Yampa, for example, it's, in the case of Yampa, it's a double. It could be like, technically it's a positive, conceptually it's a positive real or a non-negative real. And in practice, it tends to be like a non-negative double. But we just use a double. And for streams, again, it could be a natural, but we just put an end. Right? And now we can start talking about temporal transformations. And instead of adding delays or whatnot, we kind of took a step back and thought about transformations in terms of the stream as a whole. So if you think of something that varies over time, one of the very common construct in these languages is that you want to determine the value of something based on the values that you had in the past, right? So for example, the position of your player is the position where it was, except a little bit to the left if your joystick is that way, and a little bit to the right if your joystick is that way. So you kind of like update in some way. And it's very common that you express the values of things in terms of the values of the past. What does that mean, though? Like if you have a signal or some sort of time-varying entity, what does it mean to talk about the past? Well, what it means is that you really shifted the thing towards the future, which is a bit ironic, right? But to make a value of the past available at this time, you need to shift the thing to the right. And when you do that, you leave a gap. And then the thing becomes kind of like a bit undefined at that time. So the way that we kind of solve that problem, and this aligns fairly well with how these frameworks work in practice, because we need something that will be able to implement things on top, so we need a practical solution, is that we define a notion of concatenatable reactive entities. Reactive entities for which we can talk about chunks or portions, and then we can kind of put them together. And there's a mathematical definition of this, but the practical side is that one, that concatenation takes a finite chunk and presumably an infinite one, and then it kind of puts them together. And the constructor for the finite ones takes the duration of the finite entity and an entity, and it gives you just that chunk. So it kind of like segments a larger one, a larger reactive entity, and only takes a portion of it. And now we can define something like this, right? So we define, this is the definition of a counter, something that goes 0, 1, 2, 3, 4, 5, and so on. So we define a finite entity by saying that we have a reactive entity that is constantly 0, and we take one time unit from it, and that gives us a chunk. And then we kind of recurse over that definition. So the first portion is going to be 0, the next one is going to be 1 plus what we had before, the next one is going to be 2 plus what we had before. So it ends up drawing a picture like this, right? At the beginning, this portion here is that one over there. And when you recurse, you kind of add 1 and then shift it to the right. And then add 1 and shift it to the right. So this is the add 1, and this thing will shift it to the right. And that's how you end up with that piecewise signal, right? Now, if I go back to this signature, you'll see that all I am assuming about it is that there's a notion of concatenation, that the values meet the type constraint of the reactive entity, that time is a number because I'm saying 1, so it's got to be a number, and that the values are numbers because I'm saying 0 here and 1 here, so I have to be able to operate with them. Is time continuous or discrete? Is time linear or branching? There's no assumptions there, right? And that means if you interpret this thing in a stream with a stream backend, then this is this succession of values 0, 1, 2, 3, 4, and so on. But if you interpret it in Yampa, this is the piecewise signal that is 0 for a one-time unit, 1 for a one-time unit, 2, and so on. So if you sample really slow, if your time deltas are really small, then you'll see that the value 0 stays on for, like the signal stays at 0 for a long number of samples because you're not advancing time as fast. It really obeys the continuous time semantic of the language. And similarly, if you can shift things towards, the right, and that means you look into the past, what happens if you shift in the other direction? Are you looking into the future? And what does that mean? So not all languages allow you to do that. Thank you. And what we provide is a drop operation in a class that captures that idea, the idea that you have something that is non-causal, where the present can depend on the future. And not all frameworks implement that. In particular, Yampa does not implement that. In Yampa, you cannot drop samples. You cannot look into the future. But in Copilot, you can. If you go to the past, then now you can look into the future. So again, the difference here is that you're not concatenating. You're just trimming a chunk of the reactive entity. So you just need to provide the time and then the entity, and then you get something that is shifted. Right? We just forget about the all values. And to give you an example of how that could be used, sometimes we get a signal from a sensor or some kind of information from a sensor, and we need to smoothen it out. We need to eliminate the what's the word? The outliers. They kind of like make them not as pronounced. And one way that we can do that is we can average a value by the value at the next sample and the value 2 samples from now, and then we consider, we smoothen things a little bit. And that's how you write it, right? You say that the total is the average of now plus 1 sample from now plus 2 samples from now divided by 3, and that's it. And again, what we're assuming is it's non-causal because you're using drop. Time is a number because you're putting 1 and 2 here. And then that the values are fractional because you're dividing by 3. And that's it. It doesn't tell you any more than this. It doesn't tell you that it's stream-based. You could do this in a framework that allows non-causality if it's continuous time, which there are some, right? So we have backends for 3 reactive programming implementations. We have one for Yampa, one for Copilot, and one for Dunai. We almost finished one for Clash, but we didn't. But we're right there. But Copilot has an FPGA backend, so we just by using the abstract interface, we can already target hard real-time C, simulation, interpretation, FPGAs, and so on. So it's pretty useful already. But I'm sure that we can implement more, and then it will be more useful for the community. This is part of a larger context. We have a couple of projects at NASA that I invite you to check out and participate in. They're called Ogma and Copilot. Copilot is a runtime monitoring language that generates hard real-time C. And Ogma is kind of like Copilot on steroids. It allows you to deploy Copilot in flight software and stuff that is really used in missions. And the current state of things is that we're trying to implement more of the Yampa libraries and more of the Copilot libraries on top of this abstract framework so that we can reuse more. One thing that you may have noticed is that when we talked about this, here. When we talked about this was pretty darn complicated. And there's a reason for that. Copilot is a language that was designed by use. It's a language designed by need, not by value. We added features to the language as we needed them. And it turns out that when you step back and try to analyze things from a formal perspective, they don't quite fit. So maybe we need to redesign Copilot so that things mathematically make a bit more sense. And so it is informing the next version of Copilot. That's what I was trying to come to. And one more. Yeah. And we're at the point that the next thing that we'll try to implement is temporal logics on top, like a backend for temporal logics, because that's a pretty weird one, right? Linear temporal logic is future-looking only. So, well, it depends on who you ask, right? Some allow past time and future time, some only allow future time, but it's unlike the ones that you saw on the screen. Most of them have a past direction. That's everything I came to say. I'd like to hear your opinions, comments, questions. Thanks, everyone.
Thank you very much. Questions?
Hi, Alexei Radl, Google. It seems pretty obvious that if you have a continuous time functional reactive language, you could write down a system of ordinary differential equations in it, and the language should evolve them. Do you know any systems that use sophisticated integration techniques to do that, like Runge-Kutta instead of Euler?
Not really, no. So
is that even like a thing that makes sense to think about?
It is a thing that makes sense, and it is a question that comes up. So Henrik Nielsen, who created Yampa, at some point explored the notion that he called functional hybrid simulation. And the idea was FRP extended with differential equations. Yampa supports, it doesn't really try to solve the equations, but you can write the equations and sometimes they cannot work. And for example, I have examples of like basic planetary systems simulated in Yampa. You just write the equations of gravity and you hit run and it kind of works. Because sometimes they resolve right. Then there's Marc Pousset, I think he's at INRIA, has worked on, I think it's called Zelos, which is a language that incorporates differential equations, and it's reactive and so on. It inherits ideas from Lustre, but then incorporates differential equations. So maybe that helps.
Yeah, thank you.
Thanks.
Vasil from Chaos. I would like to ask why there is a hard limit on the time in the zero, because you could have, for example, time after Christ, before Christ. You could move before zero and go negative. Why there is a hard limit on the zero? Is there a limit?
I don't think it is needed. I think probably what happened is that all the examples that are there had a time, like a starting point at zero, but it would make sense to explore before. And there was some work done by Christian. Do you remember his name? He was at Twente. He was working with Jan Cooper. He had a system that was similar to functional reactive, but he was right before me. So it was a similar system to functional reactive programming, but you could go back in time before zero. So I think it absolutely makes sense.
If you have some repeating sequence or something that repeats, like sinus, cosine,
yeah,
it could go back in time and go forward.
Yeah.
No, there is no limit.
Yeah.
For that.
I think
only infinity of some types like that one float, but
I think you're right. I think we need to look into it. Absolutely. Yeah, and if you have a practical example of a language in which that comes up, I'd like to know about it. Yeah.
I don't have. Just I have example from the history, which is before Christ and after Christ. Yeah. And maybe there's problem 2000 before the problem and after the problem.
Yeah.
Also. Thank you.
Thanks. One more question? Yeah.
You've introduced a number of type classes that. And also explained that the things that implement them all have kind of different semantics. And I'm wondering if you have rules or laws that go along with them, that someone who makes a new FRP system, they can say, oh, mine definitely can be an instance of this type class or not. Whereas I think sort of what you've described so far feels very intuitive. Oh, mine kind of has a notion of the future or the past, so maybe I can implement one or the other of these type classes.
So if I understand your question correctly, I think if you look at the paper, you'll see the answer to that. Because what we did was first lay out the mathematical framework, and then try to explain the denotation of those functions and those interfaces in terms of that framework. And then we give the instances. So that's why I say it should inform the next version of Copilot, because we should step back and try to think about the mathematical ideas. And I think that's where
Thanks. I'll take a look at the paper.
Yeah.
Go for it. No, go for it.
So Christian by QB Logic. Why this one in Yampa? Why does it map to one double? Why not epsilon? He said if you sample it, you can see 0 for a very long time, but it was very unclear to me why. He said, well, one time step. Why doesn't? And he said in Yampa, well, it matches to double. Why does not match to the smallest double?
Wait. I'm not understanding the question.
So in your counter, in this example about counter,
yeah,
right? Why is that one not the smallest double value, basically? You said it's one unit.
One is one time unit.
What's the smallest unit in Yampa?
Well, in the case of Yampa, that would be, okay. So it's not 1 second. Like the way that Yampa operates is that when you run it, you provide the time. And the time doesn't really have to be real time. The time is abstract. So what I mean when I say one time unit is I mean one in that abstract domain. Does that make sense? Like Yampa doesn't control the execution loop for you. You do. And you decide if one means 1 second, 1 year, and so on.
Okay.
Does that make sense? Does that answer the question?
Yeah, I guess, yes.
All right. Thank you very much. Let's thank the speaker again. While our next speaker gets set up, I just want to remind you that you could submit lightning talks. I think if you wanted to do that, maybe contact Nikki or send a message on Discord or something. 5-minute talks, right? Yeah, so there's still slots available for those. So if anyone wants to do that, then you're more than welcome. Yeah, I recognize that feeling, all right, yeah.
Sorry about this.
No worries.
How's that? How's that coming through? Did you say something? Yeah. I'm going to keep talking for a moment while they test the microphone. How's that? Perfect. Ah, fantastic.
All right, great. So our next speaker is Sven Markiti, and he's going to tell us how to not lose our sanity.
Yeah, I love not losing my sanity. Anyway, hello everyone. I'm Finbar. I'm a PhD student at the University of Warwick, and I do FRP stuff. Normally, I work with type-level stuff, but today I'm going to tell you about my new nemesis, the loop construct in arrowized functional reactive programming. Since we got a bit of an introduction to AFRP in the previous talk, but I'm going to show how we construct such a program with an example. So here's a robot I found, and what we're going to do is we're going to try and write a program to grab an object. What we've got on this robot is a distance sensor, which determines how far away an object is. We've got a touch sensor that determines how much pressure something within the grasp of the robot is exhibiting. So if there's already something in there, it's probably going to read something because it's being pressed against. And then we've got some kind of motor to control the grip of our robot. So since we're writing a reactive program, the question always becomes, given my sensor values at some time step, some point in time, what output should I produce? And you might think and sit there for a bit and decide to write a program that has a structure kind of like this, where you've got your readings coming in as a stream, You've got predicates testing whether this is an object and whether you're already gripping an object, and then combine those two results to determine whether or not you should be setting the motor to grip or not. This is also the format of diagram we're going to use throughout the talk. This is a very heavily diagrammatical talk rather than code, because code for explaining program transformations is not fun. But yeah, so the question then becomes, how do we actually implement this in a framework like Yampa? So here we go. Yampa represents these programs as what are called signal functions. So the type reads a signal function, which takes in inputs at each time step. So for example, a pair of int here to represent the two sensor values that we have, and produce outputs. So for example, a single value referring to how much we should grip how much the motor should be working. And because it's arrow-wise functional reactive programming, we use arrow combinators to build our reactive programs, which is fantastic for reasons that will come up soon. So for example, the R constructor lets you build a reactive program from a pure function, running that pure function on each input to produce each output. So you might implement that isObject box that we showed earlier. We're using boxes as our sort of computations here, using a simple Boolean predicate. Then we have parallel composition, which we're representing as two boxes vertically adjacent. So here you might implement the two predicates that we were working with as a parallel composition, taking in a tuple input, which we split across the two things, and producing a tuple output. And then finally, we can sequentially compose using the sequential composition operator. I don't know how you would pronounce that, but we're just going to call it composition, which lets us build the example that we showed. It's saying we've got parallel composition, we've got sequential composition. We did it. We built this program. Isn't that great? Except there's a lot more we can do. Currently, we've built programs where our outputs rely solely on the input at a given time step. So for example, or like in the example we showed. But we're reacting to a stream of inputs. So what if we wanted to look at values from the past rather than just values from the present? Well, for example, here you might want to implement something like a sum of a signal over time, taking in all of the inputs and adding them up. Well, let's try and do this intuitively, and then we'll show how to build this within Yampa. So first of all, you might note that the sum of all inputs is equal to, at some time step, is equal to the sum of all inputs at the previous time step plus the input that we now have, which makes enough sense. We know how to implement this now. We could just use the R combinator, job done. But how do we get this previous sum? We need, oh, that was a good animation. We need a notion of a back edge and a delay operator. So we need some way to say, OK, we've got a stream of inputs. How do we look at the previous input? And that's what we're getting here with this delay and back edge. So that's what we need from Yampa. We need, well, yeah, for our AFRP. We need a way to provide back edges, and we need a way to provide delays. So let's do that. So to implement this program, we'll start with the same idea as before. We've got a pure function being lifted here. The only, this is exactly the plus node that we showed in the earlier diagram. The only difference is we have to do this explicit duplication because you can't, we've got this sort of split wire in the little diagram up top, but you have to do this explicitly in Yampa. So that's how it is. Then we're going to add a delay operator. The delay operator in Yampa is called pre. It prepends a value to the front of a stream, thus effectively delaying all of the values in that stream by one time step. So if you got 1, 2, 3 as your input to pre-0, you would get 0, 1, 2 as your outputs of the first 3 time steps, and the inputs the first 3 time steps, and the outputs the first 3 time steps. Oh, yep, that's what it says. And then finally, we need a way to introduce cycles and back edges into our program, which is where loop, my least favorite combinator, comes into the fray. Loop takes a 2 input to 2 output signal function, and it attaches that second output back round to the second input, thus creating the cycle, implementing the program that we talked about before. Hooray, we can sum up values now. Isn't that great? So I guess the question you might have now is, that seems fine. Why am I so annoyed by it? I've just introduced ways of making programs. Why is it such a problem? Well, the answer comes when we think about how we execute these programs. So when we look at a program written using loop, it kind of looks like there's a dependency cycle in here, which is not ideal for running programs. If we wanted to run F, then OK, sure, we need its inputs. Great. How do we get that? H. OK. Pre. OK. G. OK. F. Wait, that's a problem. We can't implement this, which obviously is not ideal. But fortunately, the important thing to note here is that pre is able to provide an output at the given time step without its input at that time step. Because it's outputting a previous value, we've already got it. We're great. We have no problems here. So what we can do to execute this program and thus break the dependency cycle is get the output from the pre, which we know, no problems here. And then we just run H, and then F, and then G. And G's output gives us the input to that pre that we will need at the next time step. So we've completed the cycle. Great, we can execute this. It was a bit of an irritating thing to work out the execution order, but it's fine, we got there. Except there are lots of different ways to specify loops, and they all have different execution orders. These two programs are in fact isomorphic to one another, but they have slightly differing execution orders where you're trying to find that pre and execute, go around afterwards. And there are going to be examples later where it's not even a case of finding one pre. You need to find multiple pre's in order to generate enough outputs so then you can actually run your whole loop, which is a pain. And then sometimes you get loops that can't even be executed at all, where you've forgotten your pre or whatever. And this is an easy enough thing to do, where you get that dependency cycle I illustrated earlier. So with that in mind, how do we actually execute these then if they're such a pain? Well, Yampa uses a circular definition to do so, effectively saying that this looped value C, we don't have access to it yet, but we will do at some point, hopefully, fingers crossed. So we'll just state it as sort of a relationship between the input and the output. We'll execute F as much as we can with A, and maybe we'll get some C out by the end, and then we can execute the rest of the loop, and we're golden. This means it has to be executed lazily, which means what we're doing is we've got this working out the execution order process happening every time you run the function. So every time step, you're using lazy evaluation to work out what the execution order is and then run your program, which seems a bit silly given that earlier we were able to just look at the program and point out the execution order that we needed. So can we avoid this? Can we take our loops and transform them into strict versions with known execution order, thus meaning that we don't have this overhead of lazy evaluation every single time you want to run your loop? It just works. And the answer is yes, that's what the paper's about. Spoiler. So what we need first is we need a strict loop variant in order to be able to transform our loops into that. We use what's called loopd. It's present in a few places in the literature. Yallop and Liu are sort of they're the ones who made the canonical form of loopd. There's some mention in some earlier papers, but they talk about it the most. And the key thing with loopd is that right before that second output, there's a pre. So we know what the execution order is here. We just get the output of the pre, because as we said, we already know what output we're producing, and then just run F, and then congrats, you've got the input to that pre again for the next time step. So brilliant. We know what we're doing. We know what we're aiming for. How do we get there? I'm not going to present the whole transformation because there's a lot of awkward cases, but I'm going to talk through a few examples of what loops we transform, how we transform them, how we apply the rules, and so on. So let's look at this loop, which I transformed earlier. The top one is the one from an earlier example, and then the bottom one is very slightly different. As you can see, we've managed to get this pre in the right place. If you sort of squint a bit, these diagrams are isomorphic. We get the same program. So for a very lukewarm version of program equivalence, yeah, these are equivalent. Certainly this holds for Yampa. But how do we formalize this equivalence? I don't want to sit here as a programmer and reorder all of my loops so then they successfully fit this scheme. Well, the answer lies in the arrow loop laws. By using the arrow combinators and arrow loop combinators, we get access to a bunch of laws which prove program equivalences. which is fantastic. This is the sliding law, which helps formalize this, which lets us formalize the intuition that we just showed. What we have is we have this second x component, second meaning it's just in front of the second input. It's just affecting the second part of the, I've got to keep on saying the word second. Like in this example here with h, you're applying h only to the second input to produce the second output. The first input is unchanged. And what this means is we're able to move something that's just before that second output of the loop and move it to be in front of the second input of that loop. To show this at work, because I think that explanation was terrible, here is the code for the loop example before, but with the two parts of our rule highlighted. And then that's what happens when you apply the sliding law. You move that h out of the way, thus meaning the pre-v is in the right place. We get a loop D. So brilliant, that's what we've got it. We've got a strict form of loop. And presumably, right, we can just apply this to all of our other loops, move the pre's in the right position, and call it a job well done. Yeah, absolutely. Let's look at another example. Wait. So this example can be run as well. This example is executable. You can run the pre to produce your outputs, and then run the G, and then that gives you your input that you require for F. But we can't move the pre. The pre is stuck in between these two larger blocks. We can't apply the sliding rule that we just did. So, oh no, we're kind of stuck now. But luckily for us, well, I say luckily, it's a bit of a cheap solution, but it is one that we're able to use. This can be expressed as a second strict loop variant, which we call loop M. The M stands for middle, where we just have this pre in the middle, and we can execute it as I described. So you might now be thinking, hold on, that seems like a really weird counterexample. Is this the only kind of loop that's written like this? And the answer is no. You can write other versions of loop. You can write other more complex loops which can be transformed into loop M's. For example, this. This one has a much more complicated execution order in that you have to run the two pre's, and then you can run I, and then you can run G, and then the rest of the loop is available to you. So you're suddenly looking for multiple pre's rather than just a single one. What I'm going to show you with these next couple of slides is this pre-x and pre-y can be sort of smushed together to make pre-xy, thus looking like a loop M. So how do we do this? So we present a new rule called split. Split follows from a bunch of arrow laws, so I guess it's more like an operation than a rule. But anyway, what split takes some term f and attempts to transform it into FL, compose FD, compose FR, where this FD is just a stack of pre's. So to see this at use, we're going to just show the steps that you would apply. There is a formal definition of this in the paper. So if you like that, yeah, look at the paper. So first, we're going to consider each of the concurrent parts separately. We're going to split them up. As you can see, we've now moved these pre's into the middle, so it satisfies what we're trying to do with the split rule. We're taking the pre-x and the pre-y here are the FDs that we showed in the earlier example. Then, because this is all just like substitution, we're going to substitute these split terms back into the parallel composition we did to get this. Now, we get to use a nice trick here. In CCAs, you don't need to worry about what CCAs are. In short, Yampa is a CCA. There's work about this. But in CCAs, parallel composition distributes over sequential composition. So you can write it, you can move the parallel compositions within the sequential compositions to get something of the form that we were expecting from split. We've got that FD in the middle, which consists, again, of only pre's and parallel compositions. Then we can merge these pre together using what's called the product rule, again, another thing from CCAs, which then finally gets us what we were looking for. We have produced a loop M from that weird-looking loop we had before. We can now execute it strictly. We've ordered its components, and we're good. In the paper, there are a fair few other transformations and some more complex examples of loop. So if you enjoy diagrams and watching me lose my sanity, have a read. It'll be fun. Unfortunately, the diagrams in the paper are not animated like on the slides, but you know, apparently I wasn't allowed to do that. Anyway, so for the rest of the talk, I'm going to mention briefly our implementation called 7. We've cut a few details, but again, they're in the paper. Have a look if you're interested. We represent our programs as a GADT. Most of the constructors actually sit in a separate GADT. You can see we've got parallel composition and pre's and R and all that in there, but we're missing composition because we put this in a separate GADT. The reason we do this is pretty simple. As we mentioned earlier in the talk, sequential and parallel composition distribute, which means that there are lots of different ways of encoding the same program. To avoid this, because that's a nightmare for pattern matching, we force the sequential compositions to be at the top level. We also provide smart constructors, so you don't have to do this yourself, but in the GADT form, those sequential compositions are at the top level. Then we just implement our rules as basic pattern matches. So the rule up here is a slightly more complex version of the sliding we introduced earlier, and our implementation just looks like this. So it returns a maybe because we don't have brain, come on. Because not all transformations can be applied to all programs. Then we're going to take our input term and split it. We've got this head-tail, which is takes a sequence of compositions, gets the first one, and gets the rest of them. So head-tail, we've got the first part of the composition chain, and then the rest of them. And then finally, the other side is just the other side of the rule. Like, once you've got past the difficulties of finding the rules and working out how to apply the various arrow laws, you just write the Haskell code as the laws fall out. So, finally, I've presented all of these rules. I've presented this transformation idea. I've presented, we're going to make this strict. Was it worth it? Maybe not for my sanity, but like, was it worth it in terms of performance? And the answer is, yeah, absolutely. So we've got a few examples to show. There's more in the paper. The first thing we did was just to make sure that we didn't break non-loopy programs, we tested a large chain of Rs. We got a 1.6, or 1.7 rather, x speed up on that. Also, as we tested with various different lengths, so smaller, shorter chains, longer chains, that speed up continued to be above 1. So far, so good. Then we tried the same again, but with a loop D. The transformation found this loop D and then gave us a 1.5x speed up, which, again, is a really good result. Same again with loop N, with a 1.7x speed up. And then finally, we did a slightly different test. Yamper is very, very good at optimizing chains of Rs, where if you've got lots of Rs together, it manages to merge them quite nicely. So we deliberately tricked Yamper. We deliberately separated those Rs with various pre's, so R pre, et cetera, and got a 1.9 speed up, which I'm quite proud of, honestly. It's quite nice. So in conclusion, what we did was we took these loops. We were like, these evaluate lazily, which is generally fine, but given how much we're evaluating it, and given that we're using it to work out execution order, could we do it strictly? And we showed that, yes, you can, and it does improve performance. In the full paper, we've got a couple of extra things that you might enjoy. As I said before, there are some more complex transformation cases that we didn't cover in this talk, and we bring this all together into a full transformation. Those are present in the paper with diagrams, because diagrams are much better than code for this kind of thing. We also proved that the transformation is correct. So both in terms of the operations we run are valid because of the arrow laws, and we proved that in pretty much every case, please don't ask me about proc notation, any loop which could be executed can be transformed by our transformation. We also do some random loop generation using Hedgehog, where we randomly generate programs that are executable loops. We use them to test correctness, so making sure that Yamper and Hedgehog perform in the same way, and for performance, to make sure that we're still getting performance speed ups even on non-synthetic examples or non-constructed examples. And then finally, we have a long section about limitations in future work, particularly because by virtue of some of the arrow laws we use, there are some forms of AFRP, such as monadic signal functions, which have a bit of a harder time being transformed. So we discuss how that might be better in future. And with that, I'll finish. So thank you very much for listening.
Thank you very much. Questions? Oh, there's lots of questions.
Oh, God, what have I done?
Very quick clarification, Ben Gamari, well typed. Loop M seems strictly more general than loop D. Is that true or not?
No, because so loop M fixes the position of the pre in the middle to be of full height, and then loop D fixes the position of the pre to be in the bottom.
And you can't rewrite the latter into the former, introducing like an identity arrow at the beginning, moving the beginning, you know, the pre.
I don't think.
You don't think so? Okay.
No, I don't think so. We can talk about this, but I think I'm not convinced we can.
Okay.
But that's a really good question. Like, I thought about that for a bit, thinking, wait, are these the same? And I don't think they are. But we'll talk about it. Hey, yes.
Hi, how's it going? Ben Bellick. I'm here as a Summer of Haskell contributor. And I was wondering, I mean, you talk a little bit right there about how the transformation is complete, right? Like any loop that you can successfully compute in the old style, you can do in this new style.
Yeah.
And I'm wondering if over the course of this transformation, you're also able to always recognize when you have loops that you wouldn't have been able to compute. I mean, you suggested before that that's one of the issues that's apparent. So once you do this transformation, does that arise somewhere maybe at compile time or?
So it does arise. It does arise when you run the transformation, just because, to be honest, it tries to do a from just, and none of the transformation rules apply, so it gets a nothing and it complains. So yes, with the exception to prop notation that I brought up, if you give a loop that can't be run to this transformation, it will error, or it will error when you transform it, rather.
I see, and that's decisive. If it gives that error, you know that it's not a possible
yes,
situation.
with the large prop notation asterisk, and yeah.
Ignoring the big asterisk.
Yeah, it's quite a big asterisk, to be honest. I'm happy to talk about it, but it's just...
I won't make you talk about it, so. All right, thank you.
Thank you.
Hello. Just a quick question. Are there any cases in which your transformations have resulted in a decrease in performance in loop execution?
We've not found one. So we, again, this is the natural case. So we tested all the things I showed you on the slides. We also tested some nested loops as well. We didn't talk about that in this talk, but nested loops were a particular headache, but they still give a performance speed up. We also did random testing, which means that we haven't found an example that breaks yet. I can't say with 100% confidence that, every loop is improved. I'm so good at programming. But certainly from what we found, we have yet to see a decrease in performance.
Thank you.
So this is Ivan Perez from KBR and NASA Ames. So I've been maintaining Yampa for 14 years, and loops give me headaches. So your pain is totally justified. And as of the last release from last month, Yampa now includes benchmarks. So it sounds like it's about the right time to evaluate the solution and see if we can put it in.
Yeah. So the prop notation thing really irritates me, and I don't know whether that's something. Well, okay. So I think you could probably have like a slight variant of loop that's okay with failing in the prop notation case, and then just include that in Yampa.
Mm-hmm.
And I think that would work really well. But yeah, absolutely, I'd be up for that.
And did you evaluate loop pre at all? You know about loop pre?
Yeah, which is loop D, effectively.
Kind of. Yeah.
No, we didn't particularly look at loop pre. We didn't compile, we didn't build any examples and then transform them into loop pre's.
Mm-hmm.
We just tested loop versus our post-transformed loop.
Yeah. From a formal perspective, going for a loop is the right thing to do, because loop follows the continuous time semantics or obeys the continuous time semantics, and loop pre breaks is discrete.
Yeah.
So yeah, it is the right thing.
Cool.
Thanks.
Brilliant. Thank you.
Any other questions? Simon?
Hello.
What would happen if you just provided loop D and you didn't provide loop? So in other words, rather than requiring the system to do it, you say, programmer, just the only loops I'm going to provide you are ones with the delays at the end.
Mm-hmm.
Would that be insupportably bad from a programming point of view?
I honestly don't know. So I thought about this a bit. So Yampa provides loop pre, as Ivan said, which is very, very similar. And people have used it and have been okay with it.
Okay.
But I imagine that in situations, so I know I keep doing this big prop notation asterisk, but I imagine in situations where you're using something like prop notation where you're not explicitly making a loop, you're almost implicitly making one, this loop transformation would be really useful because you have no control over saying to the programmer, hey, please provide a loop D or else. So I think those are the sorts of situations that make it worth exploring loop transformations rather than just going to the programmer and saying, fix it.
I thought you were going to say something about modularity, that you have a loop, but there's somewhere in some function you're calling to build the loop. Deep inside there is the pre.
Oh yeah,
And
that is a far better answer
because
than
you've got a lot
I
of
gave.
experience of writing arrowized code. Does that happen? Or do you always know when you're building loops? You know where the pre is. No. Okay.
You have no idea, and it's a nightmare to figure out where it has to
Okay, I mean, it's important to know that there is one, otherwise you're going to deadlock, right? And that's your error.
Yeah, exactly.
Right. So you've got to know something.
It happens all the time, and I avoid loop as the plane. I don't use loop at all. I only use loop pre for that reason. Because I can't figure out something that I started the program, I can't figure out where to put it so that it will resolve it.
I see. So I guess so you're saying it would be a bug, not a feature, to eliminate this and just say, use loop D and that's it. That would be a feature, not a bug. For you.
I'm not sure.
Yeah. No, but it's a really, really sensible question. Yeah. Like, sort of, people have trucked along using loop pre for the most part, but this is an improvement, and it's a nice improvement of that. So I think it is worth the effort.
Thanks.
All right.
Just to clarify, so loop pre is...
If you wanted to speak into the microphone so that people...
Oh, yeah.
Just to clarify, so the way that loop pre works is that you insert the sample. So it's kind of like...
Eat the microphone.
Yeah, I need to eat the microphone. Yeah.
Eat it.
So the way that loop pre works...
I know it's lunch soon.
The way that loop pre works is that you insert the sample. So it kind of breaks the continuous time understanding of Yampa. So it's kind of like we use it because we have to, because otherwise we can't make sense of the program. Yep. But using loop pre should be avoided if you want to write FRP, like proper FRP as Connell would define it.
I mean, no loops at all would be so nice, right? From a dependency resolution perspective. You just run it left to right, job done. That's great.
All right, so let's thank the speaker one more time.
Thank you.
Don't forget about the lightning talks and enjoy lunch. Hello. Hello, everyone. Welcome to the second session of the Haskell Symposium. Our first speaker is Patrick Redmond from the University of California, Santa Cruz, and he's going to present the paper, An Exceptional Actor System. Please, Patrick, take it away.
Hi, can you hear me? Thank you for coming. I'm going to speak fast, so wave at me if I'm speaking too fast. Okay, I will endeavor not to. As Facundo said, I'm a third-year PhD student at the University of California, studying with Lindsay Cooper. And today I'm going to tell you about how to implement an actor system in like 10 to 20 lines of Haskell code. So we're going to implement actors. Actors are nodes and message passing, more or less. Except today we're going to do the message passing with exceptions. And we're going to do this with ingredients taken from the GHC runtime system. We're not really adding anything. It's all already there. So the plan is, I'm going to do a brief review of exceptions in Haskell. Then I'll talk about distributed systems and actors a little bit. I'll show you the implementation, and then hopefully have time for a demo. Everybody loves exceptions. Divide by 0 and resume, and you're fine. Who here is familiar with exceptions in Haskell? And who here is familiar with asynchronous exceptions in Haskell? Okay, that's like half of the people that just raised their hands a second ago. There's 3 different kinds of exceptions in Haskell: imprecise, synchronous, and asynchronous. We're mostly going to focus on the last one. I'll just go over them really briefly. If you're new to Haskell, this is a little bit overwhelming. And I took 10 years before I took a look at asynchronous exceptions. But don't panic. We can classify them fairly easily by where they come from. Imprecise exceptions come from pure code. They bubble up to I/O, and then you can catch them there. We're not going to talk about imprecise exceptions for the rest of the talk. Synchronous exceptions come from I/O code and are caught in I/O code. And there's a trend. And asynchronous exceptions come from other threads and are caught in I/O. That's the trend. They're all caught in I/O. From the I/O perspective, they kind of all look the same. But they come from other threads. That's a bit different. They're originally introduced to deal with thread cancellation, meaning that they're a termination signal. When you get one of these asynchronous exceptions, you should crash, or you should regard yourself as about to crash. The conditions under which you might get them is you're running out of memory, you're running out of heap memory, which is a different limit, apparently, or you've been canceled by another thread, likely the main thread, whoever your parent is, or Control-C has been pressed. So let's go through a brief example. Synchronous exceptions, in this context, we want to know if you acquire a resource, use the resource, and release the resource, are you going to leak things? And so that's the question we want to know. Can we jump out of this code block in any way without releasing the resource? And of course, everybody here who raised their hand and understands exceptions can say confidently that, yes, if you get a disk on fire exception in the middle of using the resource, then you will jump out of this without ever executing release. And so this is no good for synchronous exceptions. And so we might add a bit more complexity here. And anybody who has looked at the source code of Base, particularly the exception module, might recognize this as about like 90% of the bracket function, substituting some implementations in. But if we change the code to look like this, where did my pointer go? There it is. You might acquire the resource, go over and use the resource, and if you're lucky, get down and release it. And if you're unlucky, well, you catch and you release it. You rethrow the exception, and that prevents you from releasing it a second time. So this looks good. Can we leak the resource? And you're all probably saying, well, no. At this point, you've solved it. Now let's throw a wrench in the gears. We're only going to talk about asynchronous exceptions for the rest of the talk. Can this leak the resource? Can somebody tell me if this is going to leak the resource? Just shout it out. Yes. Yes. Where should I draw all the little bombs? Yeah, everywhere. It can leak the resource here, 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 and here. No, so in this case, before and after using are going to be under the catch And so those will not leak because they'll go in here. Oh, I see the projector is a little delayed. They'll go in here and they'll release. But the lines before applying the catch and after applying the catch, or the spaces between lines, could be places where the runtime would raise an exception and then you would not release the resource. And at this point, why don't we just give up? I mean, I understand mask exists, but this is a bit too much. I don't want to write code looking over my shoulder all the time. So now for a brief interlude into distributed systems and the actor model. So when we're talking about distributed systems, we often draw diagrams like this with a big arrow pointing down that indicates time. And we label processes. So this is process 1 running a long-running task. And sometimes you might want to not run the task yourself. Perhaps you have other work to do. And so you might send a message with the lateral arrow here to another process and have that process run the task for you. And then when that process finishes, it'll send the message back to you. And message passing is pretty important in distributed systems, also in actor systems. We can use these diagrams to also talk about actor systems. You just change the P for process to T for thread. And now instead of sending a message to an existing process, let's say we're forking, we do the long-running task, then we get a result back in the form of the other process quitting, which is like the other thread quitting, which is like a join. But let's say you care about whether or not the long-running process is taking too long. And so you have a timer. And at the end of the timer, you send a kill message over to the other, you send a kill to the other thread. You have this in Haskell in the control.exception or control.concurrent library called killthread. And it's implemented with throw2, which throws the thread killed exception. But as we've shown above, you can catch exceptions. So what if you just didn't get killed when you were asked to be? What if you just didn't do what you were told? Well, yeah, you can catch exceptions. You can do what you're not told. And you can do it a lot. I mean, what if we had a whole bunch of threads and they were all just saying, well, I'm going to catch these exceptions. I'm not going to do what I'm told. This is starting to look a bit fishy. This doesn't even look like exceptions anymore to me. I mean, all right, so with that introduction, now we're going to implement the actor model very briefly. We're going to use the exceptions, and I want you to interrupt with questions, because the next couple of slides have a bit of code and are a bit confusing, or a couple slides onward. All right, so we need 4 primitives. These roughly correspond to the things that Hewitt once told us are an actor system. We need to make a new actor. We need to be able to kill a running actor. We need to be able to send and receive messages. And Hewitt also, I think, said that actors need to be able to change their behavior. So we've already seen 2 of these primitives. We're going to fork IO to make a new actor. We're going to kill thread to kill existing actors. So we need 2 more primitives. We need to be able to send messages and receive messages. You can probably guess what send will be. Receive is going to be like a main loop. So on your thread, you'll fork and you'll drop into a main loop. We call it run actor here. And that main loop, you'll give it a handler. And the handler is defining the behavior of your actor. The handler will take messages, do some stuff, and then quit. And the loop will run your handler again later. The stuff that you might do is sending messages. So we're going to give you send and run actor on the next couple of slides. And all of this is already in the GHC runtime system. We're using fork IO, kill thread, throw2, and catch. We're not introducing anything new. All right, so let's do it. The first thing you probably want in your actor system, or your actor program per se, would be to define a message type that corresponds to whatever your domain is. We're not defining that here. We're just saying that it's there. And then you say instance exception, and suddenly magically it's a message type that you can send from thread to thread, because the exception system is extensible, which is really cool. And then the send function is rather simple. Hold on, let me A to reduce that. There we go. Yeah, it's just throw2 in this talk. In the paper, it's a bit more. We do some interesting stuff with that, but here it's just throw2. We're not adding anything new. So let's look at the run actor main loop. The main loop is going to take a consume function. The consume function is your function. It defines how your actor is going to behave. It's the handler that receives a message and deals with a message, does something fun. The first thing the runActor function does is it masks asynchronous exceptions. That's the other part of bracket that I didn't mention earlier when I pointed out that that was 80% of bracket. After you mask, we're dropping into a loop with an empty inbox. That's what the little empty list is for. Here's our proto loop. Our proto loop takes an inbox, and then if it's empty, goes to sleep. If it's still empty after we wake up, then we're just going to continue our loop. If our inbox is not empty, we're going to pop off the first message in it. We'll consume the message and return the remainder of the inbox. Again, looping around. I haven't said anything about catching exceptions, but this more or less handles the simple stuff. Now let's think about catching exceptions. So I've just wrapped the cases that I showed you a second ago with a catch and added an exception handler. So now we kind of have three cases if you squint. We have the case that you sleep, the case that you process one message, and the case that you get a new message and append it to the end of the inbox. If in either of these first two cases we receive a message or an exception, sorry, I'm going to start conflating those, we will drop down into the handler and simply append it. And in any of the three cases, we return the next inbox and loop around and continue. Why does this work? It's not in the type of sleep. Sleep doesn't exist, sorry, thread delay. Thread delay is too wide. It's not in the type of thread delay, but thread delay is interruptible. And it's not in the type of the functions that you're probably calling inside of consume, such as print or send or other sorts of functions you might call that do I/O. But consume is potentially interruptible, and we don't know. And what this means is, if at any point during the running of sleep, or if at certain points during the running of consume, an asynchronous exception arrives at the current thread, we will bounce out of these red parentheses down to these red parentheses and add the new message to the inbox, loop back around. That's all fine for sleep. If we're sleeping, we didn't have any messages, we weren't doing anything. We were just waiting for a new message to come. But if we were in the middle of consuming a message, let's say in the process of consuming a message I needed to send to you and to you, maybe between the two sending, I bounce back out of the consume, I get a new message, I add it to the inbox, and I loop back around. If I've done that in between, that means this X here, this one I was in the midst of consuming, didn't actually get removed because I bounced down here and used the whole inbox. So this is a buggy framework. This is a framework where you might process a message twice. In addition to that, we support a few other features in the paper. We use a wrapper data type to distinguish real exceptions from messages. And we put inside of the wrapper data type a sum exception. And the sum exception gives us dynamically typed messages and makes actors extensible, meaning that you can have them receive new kinds of exceptions without actually changing their code. We also encode state transition into the framework so that you don't need IO refs or anything like that. How am I doing on time? Chair? Time? Good. Okay. 15 minutes is way slower than I'm normally talking, so I need to do this part fast. All right, so in distributed systems literature, there's an algorithm called ringleader election. You wouldn't necessarily do this with actors in practice. It's not very useful for actors, because on a single computer, you could just generate a random number. But in the ringleader election algorithm, our goal is to pick a leader. So if you have a bunch of nodes in a distributed system, those nodes with a ring topology in the network, each node knows its successor and has a unique identifier, but they do not know the number or the identities of anybody other than their successor. The ringleader election's goal is to find a leader, which is finding an extrema in this ring. So the way it starts is any node decides to start the election by nominating itself to its successor. It's the only thing it really can do. Its successor then evaluates whether or not that's a better leader than themselves and forwards a nomination or produces a new one. So here, 2 has nominated itself to 1, and then 1 has decided that 2 is a better leader than 1, and nominated its 2 to 4, and 4 has said, no, 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 I'm better. So these nominations go around the ring. When we get back up to 1, 1 decides, well, 5 is better than the leader that I previously concluded was good. And so 1 replaces their desired leader. 4 does the same, 5 is better. And so we get back to 5. So now something different happens. 5 is receiving a nomination for itself, which at this point we know that the nomination for 5 has gone all the way around the ring, and everybody's best nominee has been 5. And so the algorithm is complete. So now I can show you a quick demo of this algorithm implemented using our little actor framework. Now, as I said before, the paper includes a bit of additional complexity. That is, we support stateful actors. The algorithm that I just showed you mostly just passes around a nominate message. In order to set up the topology of the ring, we also have this uninitialized state and an init and a start message. And I'll just very briefly show you the pure function that represents, or sorry, it's not pure, the pure-ish function that represents the actor's behavior. The first 2 cases, if you're uninitialized and you receive initialization, then you become a member of the ring. The topology is being set up. The second one, if you're a member of the ring and you receive a start message, then you nominate yourself to start an election. And the third one is the one that we just talked about. The third one is, if you're a member of the ring, you receive a nominee message, and you are the nominee, then that means the nomination has gone all the way around the ring, and the algorithm is complete. If you're less than nominee, then you simply forward the message, because the nominee that you received is better option. Or if you are greater than the nominee, then you make a new message nominating yourself to your successor. And that's pretty much it. Cool. So we ran it with 5 nodes, and it generated a random order that's not very interesting. Let's do a different one. That's not interesting. That's still not interesting. There we go. OK. So the random order of the ring topology is 9, 10, 8, 12, 11. And thread 7 is going to set things up for us. So thread 7 tells everybody who their successor is, and then says start to thread 9. And the algorithm that I showed you on the slides are these. I'm not going to go through all of them. But so 9 says, I nominate myself to thread 10. That's my successor in the list at the top. And then 10 says, I nominate myself to 8, because I'm better than 9. And then 8 says, oh, sure, I nominate 10 to 12. It goes all the way around the ring. It's not that interesting to go through all of these, so I'll call that the end of the demo. How did we get here? Well, in 2001, we got asynchronous exceptions in Haskell, which gave us the ability to throw to an arbitrary thread to cancel the thread. And we could only throw built-in exceptions, which is the key detail. It also gave us the ability to catch, but not just catch to clean up the database connection and then terminate, but catch and recover, meaning we could catch the exception and continue running. And then in 2006, we got the ability to take any data type and turn it into an exception with that one-liner instance exception my data type name. And you put those 2 ingredients together, or 3, depending on which you're counting, and you get this framework. So just to wrap up, this is built into the runtime. The actor ID is the thread ID. There's no channels or locks to be spoken of, except for the fact that they exist. They're just in the runtime. And there's no real imports besides things that are in base. It's just control.concurrent and control.exception, and then some bookkeeping. And you can do this with any data. Some things that are maybe not so good about this is we've opened a magical trapdoor from the land of if it compiles, it works, to the fairyland of dynamically typed spooky action at a distance with an unintended communication mechanism, which I kind of love. Duplicate deliveries are possible, but we can actually fix that by forking the call to consume. And now duplicate deliveries aren't possible because you can't interrupt the other thread, unless the other thread, who's anonymous. Anyway, you can get around that. And the sender blocks until the recipient has enqueued. These are asynchronous exceptions, sender blocks. Anyway, that's fine. You can avoid that too by forking whenever you send. And it's slower than channels. Yeah, I'm putting that under the less good column, right? This isn't a good framework. It's slower than channels. What we expect, that the unintended communication mechanism is slower than the intended communication, holds true. Except not always. If you overload the RTS with way too many threads, apparently the exceptions are faster than channels. I don't know why. Sorry. Future work. Figure out why this is sometimes faster than Chan. I have my theories. I'm not going to propose them unless somebody asks. Compare the performance with T-channel, the SDM implementation. I have no idea what will happen then. I haven't done that yet. Our paper has lots of graphs on this. It's kind of fun. Now that we have, I think, a GHC 9.61, we have delimited continuations. So we could probably implement this with delimited continuations, and then we don't have the double send issue, which is kind of fun. Because basically, I think if we catch an exception, maybe there's a way of accessing the continuation from within the consume method. And if we store that along with the state and the inbox, go back around, we can just resume that rather than processing the next message. Yeah, and maybe some future work is to limit the power of asynchronous exceptions in GHC. I'm not really sure. It's up to y'all. Thank you.
Any questions for Patrick? Please walk to the microphone. Remember to share your name and your affiliation for our online audience.
Right. Hi there. Simon Fowler, University of Glasgow. Really lovely talk, quite funny. I was wondering, do you think, so in Erlang you can monitor or link to another process where you can detect whether that process has gone down or terminated? Is there any way that you think that you could abuse the GHC runtime system to do that?
You mean detect if another thread has crashed?
Yeah.
Yeah, so this is one of the primary things that Joe Armstrong says is necessary, is the ability to detect when another thread has, when an actor, I don't think he calls them actors, has terminated. And in our case, the way that you'd approach that is by using finally on the end of the actor. So I skipped over it, but up here where I actually run these things, I'm calling run actor. And that's just an IO action, and I'm passing it into this function that sets up the topology. And so I think what you do is you'd put a finally here, and that would notify somebody who bookkeeps who's alive and who's dead. I'm not sure what actually, I haven't tested what happens if I throw an exception to a thread that has died. But maybe that causes problems and would be detectable. I'm not sure.
Okay, brilliant. Thank you.
Stephen Dillon, Jane Street. Sure. Firstly, this is horrifying. So well done. Nice work. Second, you mentioned that the mechanism is slightly unreliable because of the possibility that some of the exceptions get swallowed by consume. And you had a workaround for doing the consume in a fork IOs that happened off some other thread. Have you thought about how you might like to extend the asynchronous exceptions mechanism in GHC so that you could do these things reliably?
Thank you for the question. I think the question is, can we lean into this?
Yes, of course.
Well, okay. So for the first thing, so we're not losing an exception if consume is interrupted. What we're losing is the partially processed current message will become reprocessed. So we're losing the progress that happened. So I guess what you're saying is, can we fix that?
Yeah.
Yeah. Well, so I mean, you can fork, and that fixes it. I mean, that's literally in Simon Marlowe's paper. Is the two caveats that I gave here, credit where credit's due. Avoid by fork.io of consume and avoid by fork.io of send. These are basically written in the footnotes of these two papers. And they work, because fork.io is not interruptible. What's interruptible? I don't know. It's in the documentation. So like you can get around it. I'm not sure if you would need to extend the exception system to solve the problems, because like the tools are already there.
Okay, thanks.
Yeah.
All right, so we don't have any online questions. So let's thank Patrick once more. Well done.
I don't know if did you notice that?
I guess it got interrupted.
Hello, can you hear me? Does this work?
All right. Our next speaker at the Haskell Symposium is Abhirab Sarkar from Chalmers University of Technology, and he is presenting the paper Hasty Programming Trusted Execution Environments with Haskell. Please go ahead.
Okay. Thank you, everyone, for coming to this talk on programming trusted execution environments with Haskell, specifically a domain-specific language called Hasty. I must begin by saying I'm very glad to speak in a room full of Haskell programmers, because I've done it the other way around, like presented this to hardware researchers and hardware designers. And I had to answer questions like, what is a monad? And what is Haskell? So let's start with the authors. So I'm Abhi on the top left. My co-authors, Robert and Alejandro, are present in the crowd. And Koen could not come to Seattle, but all of them have been very instrumental in the development of this project. So let's begin with a typical cloud deployment scenario. We have a set of applications which shares some kind of virtualized hardware, and there is this invisible layer of software that lies underneath the operating system, the hypervisor, and we tend to call this the trusted computing base. We trust it that it will do the right things, and you will see the dotted line goes past the applications as well. So what I'm indicating is that there are things like the language runtime as well, on which we rely to do wonderful things like memory allocation and threading and scheduling. Now, security researchers will tell you it's not a good idea to trust this software, because there are various well-known vulnerabilities where you can attack the operating system, the hypervisor, and compromise the software that lies underneath. So what ends up happening is, even if you use a strongly typed, theorem-proven software at the top level, bugs and vulnerabilities in the lower level of the stack will result in the fact that all of the applications at the top will end up getting compromised. And hardware vendors have been thinking about this for some time, at least 10 years. And the solution that they come up with is called trusted execution environment. The general idea is that you have a disjoint portion of memory, and any kind of confidential code and data that you have would reside on the trusted execution environment. And even if there are bugs and vulnerabilities in the operating system, that will not affect the confidential code and data that resides in the TEE. So a natural question now is, how do you program TEs? So before that, I just want to say that pretty much all the well-known hardware vendors like Intel, ARM, RISC-V, all of them have been thinking about this, and they have different ways of implementing this. So for example, this disjoint piece of memory could be the virtual memory, like Intel, or it could be the physical memory, like in ARM or RISC-V. So coming to the programming of TEs, the general approach looks like this. First of all, you program in a low-level language, preferably C or C++, and you divide your application into two projects, a trusted project and an untrusted project. The trusted project is much smaller in size, and it relies on a restricted version of the C standard library, which is implemented preferably by the hardware vendor. And what ends up happening additionally, and this is present in both Intel and ARM, is you have some kind of an enclave description language that kind of defines the interface of how data will flow between the trusted and untrusted parts of your project. The project would also involve some kind of complex data copying protocol. For example, in Intel, only the first layer of pointers are copied. So if you have like a nested pointer, the programmer has to manually go and copy each of these levels of pointers. So of course, this is a bad programming model, and high-level languages have been thinking about how to do this. So some of the well-known approaches are present in Go and Java, and the general approach that they take looks something like this, which is, first of all, they extend the program. They extend the language. So both in case of Go, it has a language extension which adds a separate type of coroutine. Similarly, Java has some special keywords. First of all, you modify the parser because your language has extended. And most importantly, the compilation pipeline also has to be modified such that you can track the data flow and actually work out how the data should be partitioned. Of course, this is a known undecidable problem which cannot be done automatically, so you use judicious amount of annotations, and yeah, it's not great. And of course, the runtime also needs modification. So to tackle that, our approach is through a domain-specific language, which we devise, which is called HASTI. HASTI is simply provided to the programmer as a library. It most importantly does not rely on any kind of compiler modifications. We do not extend the language, we do not extend the parser, but of course the runtime requires certain modifications. And additionally, we include a pragmatic version of information flow control to monitor how data moves between the trusted and the untrusted sides. So to summarize, like the key contribution is, first of all, it gives you an automatic way of partitioning your program using the type system. It does not require any compiler modifications. And you get to program in a high-level language like Haskell and not C. And you can get to enforce some kind of information flow control on the data. So let me begin by illustrating you with a simple password checker example. And I can introduce the API as well. So the API relies on three monads. I'm going to start with the first one. The first one is an enclave monad. So this is a fairly simple function. It gets a password string, and it maps it inside the monad and just checks that whether it maps with the password that is already present inside the enclave monad. The second one is the app monad, which is kind of like a setup monad. It sets up the applications. Then you start with this operator, which says that, OK, this is a constant that will reside inside the enclave. So you use this in enclave constant operation. It will raise the secret string into the enclave. This operation in enclave, it gives you a reference to this function. So if you see here password checker, this is referring to the password checker above. So you get like a reference to the remote function, the enclave, and you can call it from the client side as well. Then there is a client monad. What this monad does is, it's very simple. It asks the user for a password. You get the password. And this is the interesting part. It takes this enclave reference that you have, efunc, and then it gives you a way to apply the user input, which you got here. So it applies the user input. You will see the types match here. And then the gateway function mimics something like a remote procedure call, which actually calls into the enclave. And then you return the result. So this is your entire program. This program is not written as two projects. You will notice it is just one single program. And the way we do partitioning is by compiling it twice. So the idea that we use here is that you have your original program, which contains some parts which are secret, some parts which are untrusted. And what you do when you compile it twice is when you compile it for the enclave side, you set some dummy data in here. And when you compile it for the client side, you put some dummy data for the secure part. So let's look at this program and how this one would be partitioned. It would look something like this. So if I again go back to the original program, you will see when I compile it for the enclave, this part of the program, the client side, this is simply substituted with a dummy implementation. Something like this you see here. And similarly, when I compile it for the client side, the enclave part will be substituted with some kind of dummy implementation, like this. In this case, the in-enclave function ignores the password checker body, and the compiler basically optimizes it away. So effectively, by doing this, what you have done is you have partitioned your program into two parts. And then what you can do is simply run this part of the program, which is the enclave part. You run it on the trusted runtime, whereas the untrusted part runs on the usual GHC pipeline. So if I were to show you what the tool chain looks like, so we use Cabal simply. And let's see, let me try to build it for the enclave actually. Or let me build it for the untrusted side actually. Then we can see that let's see. -f enclave. So you can see here I'm just passing a flag. This flag is indicating that compile this for the enclave. So while this compilation runs, we can look at the code. It's exactly what you saw before. It's simply the password checker code. The only thing notable here is there is this if-defs present here. What this if-defs are telling you is that when you are compiling this for the enclave, just substitute the enclave file. And whereas on the other side, if this flag is not passed, you substitute it for the client. And if I were to look at one of these, you will find that the enclave monad has like a dummy implementation down in several parts. And something similar happens there. So, okay, now this part is compiled. So if I take a look at the assembly generated here, or maybe to the binary. So let's see, object dump here. So this is the main program, and if I were to read the string parts, you will see it only stores the string secret. It's encoded in hexadecimal here. And you will see the other parts of the string, like these things, these have disappeared. And now if I do the same building, but instead of passing the -f enclave flag, if I just do it like this should ideally not contain the secret string. And we can, again, open the binary. And you can see here. So everything is hexadecimal encoded, but you can see the secret string is not present. It's just showing the strings, enter your password, your login attempted, basically this parts of the code, right? Okay, so let's return to the slides. So we have looked at how it works at the level of the binary. Now let's go a bit more at the higher level side and see what happens. So in terms of information flow control, this is a fairly simple information flow control framework, because instead of multiple labels and like a lattice, etc., we just have a low security level and a high security level. So if we were to enforce general non-interference, then you would not allow any data to flow from high to low. But we want to allow some kind of declassification to happen. And in our case, in our framework, that's done using the gateway function. So let's look at the type of the gateway function. It's fairly simple. You can see here that a secure enclave is converted into a client. And if you look at what kind of guards or protection that we have here, a very simple one that we have is that this has the binary constraint. So imagine in the enclave code, you have some kind of, like secure data, like say a private key, which you do not want to leak. So if that private key does not have a binary instance, this private key will never leak out into the client side. There's another level of security that we enforce, which is in the enclave monad, which is instead of instantiating the monad IO type class and allowing this monad to do any kind of IO effects, it instantiated a restricted IO type class where we kind of make the effects more granular, like which other effects that this can do. So those are like the two constraints that we enforce on this gateway operation. In terms of theory, we don't have a proof yet, but the general non-interference proposition for our system is this, that if you have a program of the type enclave A to app done, and given two enclave computations E1 and E2, if your program P does not have any gateway operations, then P of E1 and P of E2 will have the exact same side effects on the untrusted client. We have not mechanized the proof, but the paper goes into the operational semantics, and it can be used to prove these properties about our library. So now let's come back to the implementation. So the usual style in which we implement this, we have a Haskell application, you have a runtime underneath, and the runtime heavily relies on the C standard library for all kinds of operation. Specifically for Linux, we rely on the GNU libc library. The libc library gives you things like mmap, madvice, pthread APIs, math APIs, pretty much everything it relies on for that. So now if we want to host the enclave side of the application inside an Intel SGX enclave, this glibc is absent. But instead, what we have is something called tlibc. So all of the mmap, pthread APIs, all of them become absent. So effectively, you cannot allocate memory anymore because GHC runtime heavily relies on mmap for doing memory allocation. So in that situation, how do we actually host our applications on an SGX enclave? So our framework is kind of interesting. So we have already spoken about the untrusted and the trusted application partitioning. We rely on a library operating system called Gremlin. And what this library operating system does is when it loads data onto the enclave, it takes a hash of all the libraries that it loads. So it has a manifest file where you can state that I am relying on glibc. And what it will do is it will also load glibc onto the enclave, but it does some kind of integrity checks. So if there is an operation, a call to mmap, it will make sure that the hash of glibc matches the hash when it actually loaded this onto the enclave. And another thing which it does, it narrows the system call interface sufficiently. So instead of the 200 plus system calls, Gremlin gives you only like 40 system calls. And the 200 plus system calls that is missing, it's kind of implemented within the library system. But even then, the trusted runtime does not directly work with Gremlin. Because again, mmap is a fairly complex function with several types of operations possible. So we had to patch mmap to remove certain options which are not supported by Gremlin. Similarly, the select function call, Gremlin does not have any operation for select. And the GHC IO manager relies on select. So we had to patch that as well in our trusted runtime so that we could host this application. So this is the general framework that we have. For communication between the trusted and the untrusted part of the application, we use an IPC call, which sends and receives data between the two sides. So as you might expect, the performance is not great. So let's go to the performance. So first of all, let's look a bit at memory usage. So in memory usage numbers, this is the same password checker application, but extended a bit such that the password file is actually written on disk, encrypted, and then decrypted and read back. So the notable numbers here are that the resident memory size does not exceed 93 MB. So what is this 93 MB? The disjoint set of memory that an enclave have that is bounded by 93 megabytes. So if your memory usage exceeds that, what ends up happening is it starts swapping onto the disk. And that swaps are very expensive. Those memory get encrypted, and every time it's read back, it has to be decrypted. So at least for this particular application, this wasn't a problem, but it requires more benchmarking. As for the latency, again, in this password wallet example, we had around a 60 millisecond latency, which is much slower compared to what would happen in a native SDK, which is only around 0.6 milliseconds. Do note that the native SDK is also kind of slow because a function call in an enclave is not as simple as just making a jump. You actually have a separate enclave call instruction, which makes a domain transition into the enclave. It has to reset the registers and do a number of things. So this is one area where I think a lot of engineering can be done. For example, if we remove the library OS and actually start relying on the tlibc, which is provided by Intel SGX, we can get to a much closer speed to the 0.6 millisecond latency in the native SDK. Finally, let's talk about applications. So we have a cool application that we built. Let me talk about one of them, which is a zero trust federated learning scenario. So in this scenario, you have two mutually distrusting parties. Firstly, a machine learning model owner. They have certain models which have certain weights which they do not want to reveal to the cloud server, which is the original threat model. But at the same time, it does not trust the client as well. If it leaks this data to the client, it's afraid that the client might use that. So the client, at the same time, it has the data, but it does not want to reveal the data to the server or the model owner because it might be confidential data like patient data or something similar. So in our scenario, what happens is that we store the ML model inside an Intel SGX enclave. And what we do is we do the encryption of the model, and we send an encrypted model to the client. The client then trains the model on its end on the encrypted side, and then it sends the encrypted model back, and the aggregation again happens inside the enclave. So if you're wondering how does the client train an encrypted model, we have a homomorphic encryption library that we have also built. So what this library does is it trains the data, and it allows you to work with very simple operations like addition and multiplication. So it is a very simple model which does linear regression, but at least it illustrates the whole example of how you can do that. And you can see there is mutual distrust across the board in this kind of application. Apart from this, we have two more examples. We have a password wallet, which is encrypted. It's kind of similar to the password checker example, which I showed you, where the password file is actually encrypted. This encryption is done using, OK, thank you. This encryption is done using a root seal key, which is a key which is found inside the enclave. And the reading of the file is also done using this root seal key. So this example can be found on the paper, and then there's a differential privacy example, which is also there. Just to conclude, I'll briefly talk about future work. A very nice generalization of this kind of compartmentalized application is available in something called Cherry. So Cherry is a project which has been going on in Cambridge for, I believe, more than the last 10 years or so. This allows very efficient sharing of data, unlike the data copying, which we are doing here. And in this case, I feel like GHC is a very good target, which can be ported to this kind of hardware. And this will give you much more efficient data sharing for confidential codes. The general threat model here is slightly different from what we have seen here. Each library, they are distrusting of each other, but we do not assume that they are all going to attack, but there might be vulnerabilities in which might sweep into the vulnerabilities of the other libraries here. So again, in this kind of work, the challenge, the obstacle lies in the runtime, because Cherry makes some very fundamental assumptions on how a pointer is represented. So we kind of need to overhaul the runtime sufficiently to make sure that Haskell can run in terms of on Cherry hardware. But as a general note, I think a lot of security critical software is migrating towards this kind of model where you have compartments. And I believe Haskell is a very good source language to experiment on ideas related to this. That is all I had for you. Thank you.
Any questions for Abhirab?
Hello, Anil Madhavibedi from Cambridge. That was really nice work. Essentially, at a high level, what you're doing is that you're trying to partition a single GHC runtime to run in two independent address spaces, so two different kernels. Have you considered how to just share a part of the GHC heap and just map it into both domains? And then this way, you have kind of a shared exchange heap in which values can be written and read by one, and you can avoid having the overhead of serializing over IPC. And it kind of leads on to my second question. Do your abstractions admit having multiple enclaves? So if you have, for example, 3 of them, and you're trying to run code across something, do a map across various serializations, do all the cross compilation pieces kind of work such that you can have more than one of these things in a single application?
Thank you, Anil. I think, first of all, I'll talk about the multiple enclave setting because we saw a very interesting related talk in ICFP, which was Haskell, which was talking about distributed programming. But I think the key idea is very similar, which is that we have two concrete monads, client and enclave. But if you can parameterize on that specific client, this becomes generalizable to multiple enclaves. Again, the challenge would rather lie in the runtime, like how do we modify the runtime representation? And again, the first question which we're talking about, data sharing across two situations, I think in ARM in particular, ARM trust zone, things like that, I think there's a physical separation between those things. Even the memory buses are separated. So I don't know in such case what we will do. And I also am not sure about the threat model because the enclave's threat model is very strong. It assumes that everyone is an adversary and there is only one small portion. Whereas the compartments are slightly weaker. But so that seems like a very nice threat model to at least experiment with on this idea, the future.
Great work, thanks.
Thank you.
Hi, I'm Tadashi Saito from University of Electrical Communication in Japan. One quick question. Is your work is very depends on ZLibC. So we cannot use this with like a muscle or other than ZLibC, right?
Not really, because that's basically, so muscle allows, so we have actually played with muscle as well, because initially the model inside the enclave is you want to statically link everything and go up. And I don't think glibc supports full static linking. So we kind of tried to do that, but that did not work. But absolutely, the framework. So in the manifest of this Gremlin library OS, instead of pointing to the glibc, if you point to muscle, it is going to link those. The point is that it requires, so GHC heavily relies on mmap. So it's a problem with GHC that mmap is, and tlibc only gives you malloc. So yeah, it kind of boils down to that.
Yeah, but mmap is included in POSIX, so it is kind of portable function, right?
So not in tlibc that I'm aware of, but if tlibc, which is Intel's libc, if they provide support for mmap, and I suspect they're working on it right now, so yeah, then it would be very simple to do that. We wouldn't need to go through this library OS route as well.
Okay, thank you.
Yep.
All right. So no questions online. So let's thank.
I think Ben.
Sorry, Ben. No. Go ahead. We have the time. I haven't saw it.
Ben Gamari, well typed. It seems to me like bringing in the entirety of the GHC runtime system is that significantly blows up your trusted code base, especially given you need a whole operating system then to support it.
Yeah.
So have you thought at all about how plausible it would be to instead get rid of most of the dependence of just the enclave bit of the mutator, right, that you actually want to run. And this would also probably allow, in process, avoiding having this process barrier, which would improve performance as well. And it would be, I think, not maybe that hard, right? You just need a nursery in the enclave, and then you need to bound the amount of allocation you can do, but that's probably doable for most applications. Have you considered this at all, or is this?
So again, I'm not sure in situations like trust zone how that would be supported, where the physical placement of these things. So I believe like in all of these cases, like say the nursery, and say you have the nursery here and the older generation here, they live within the same virtual memory space, right? But in case of things like ARM trust zone, they are physically separated.
I mean, you could arrange for them.
You could arrange for them, of course, and I don't know the cost for that. But positively, there's something which we are trying to look at, and I really wanted to talk to the JH3 team about this. Like, how would I get rid of the library operating system? It was just because we are prototyping. This is like a fast path to prototype.
No, it seems
but
like nice.
That will positively, reduce the trusted code base and improve the performance.
Great.
So,
thanks.
Yeah.
Any more questions for Abhirop? All right. Then thanks, Abhirop, again.
Can I? Okay. Yeah.
Right, our next speaker is Takato Tsuka. He's from the University of Electrocommunications, and he is presenting Haskell library for safer virtual machine introspection. Please take it away, Tsuka.
Thank you. I'm Takato Tsuka from the University of Electrocommunications in Japan. And this talk, the title of this talk is Haskell library for safer virtual machine introspection. And this work, this is a joint work with Iwasaki. So let's begin. This research is concerned with a technique called virtual machine introspection, also as BMI. BMI is for inspecting the guest OS in the virtual machine from the BMI program on host OS by accessing the guest OS memory. For instance, the BMI program can scan the guest OS for a hidden process and can kill the process from the outside. By inspecting the guest OS in this way from the outside, the obtained information is highly reliable even if the guest OS is infected by malwares. However, BMI programs should appropriately interpret the hardware-level raw data as concrete data structures in the guest OS. For example, if the obtained information is a bit pattern of Windows 64, the BMI program should interpret them as a 64-bit signed integer. For a concrete example of BMI program, we present a program that obtains a process ID in the Linux guest OS by using libBMI library. For the first, in the Linux guest OS, the process ID is located in the member PID, which is a 32-bit signed integer type in the task structures. And task structure is also exists statically in the kernel as an init task variable. Therefore, the BMI program can read the process ID by accessing the member PID in the task structure from the init task variable. So this slide shows a C program that directly uses libBMI library. And there are three parts in this program. Initialization part and finalization part and main part. So let me talk about main part. The main part consists with 4 steps to retrieve the process ID. So in the first step, it obtains the address of the variable init task by calling the libBMI's API. Similarly, the offset of the member PID can be obtained by another libBMI API. Then, in the third step, the program calculates the sum of the address and offset in prior steps and obtain the PID's address. Finally, in the last step, it reads 32-bit data at the address of PID to obtain the init task's PID. Through the program in the previous slides, I want to point out two serious problems in using libVMI. The first one is reading and writing guest OS data requires complicated procedures. As seen in the previous slide, it is necessary to calculate the address of a structure member and use an appropriate API for the bit width of the member value, in this case, member PID. The another problem is that statically undetected, but fatal errors can occur easily. There are three categories for possible errors. The first one, which we call C1, is specifying an incorrect variable symbol name and structure name and member name. For instance, the tasks underscore struct is misspelled as task struct, which the underscore character is missing. The second one, C2, is making a mistake in address calculation. In this case, it subtracts the offset, which it should be added to the address of top structure top. The last one, C3, is using an API with bit width other than that of the target data types. For the member PID, the bit width other than 32 is incorrect. These two problems requires carefulness on the programmer, and it also puts an enormous burden on the programmer. In addition, such three categories of errors might induce retrieving false data on read operation, or in the worst case, a crash of the guest OS. To solve this situation, this research aims to alleviate two problems from the viewpoint of programming languages by using two approaches. One is that utilizing the static type checking mechanism to detect the programmer's errors at compile time. The another is to employ metaprogramming to make it easy to develop VMI programs. To support these two approaches, we adopt Haskell and create a library named HerVMI. This slide shows the Haskell program that obtains a process ID in the Linux guest OS in terms of HerVMI. The parts within drawer parentheses generate drawer parentheses use metaprogramming, and it generates dedicated types and accessors at compile time for reading the process ID safely. For instance, the generate struct meta function takes the structure name and member's name to generate dedicated types and accessors for the member PID. This blue rectangle shows the generated code by generate struct meta function. Also, the generate symbol meta function generates takes the symbol name and to generate the corresponding accessors for the variable init task. In this case, get init task. For intuitive use for programmers, the get symbol meta function takes the symbol name to generate a corresponding Haskell variable, in this case, get init task. And the right star arrow operator generates a snippet of code that reads the member PID in the task structure. These meta functions and meta operators are explained later in this talk. In addition to the generating codes for accessors and types, this program merges the three steps from obtaining the offset of the member PID to read its in a 32-bit into which takes 5 lines in the case of C program into a single line, as in this line. So before looking at code generation in HAR-BMI, I explained the generated types and accessors in HAR-BMI. First of all, the HAR-BMI uses data types to represent pointers and values in the guest OS. Each data type for the pointer wraps the address of its pointer, and the data types for values wraps its data. By using these data types, Haskell's type checking mechanism can statically detect every type mismatch of address and value. For the variables in the guest OS, HAR-BMI provides them as Haskell variables, as in this getInit task. And then, having declared the data types in the previous slide, HAR-BMI defines functions that go back and forth between a structure pointer and its member pointer. And by providing these two functions, the programmer need not write address calculation code. It's in their programs. And also, read and write operations are declared as class methods. And the programmer also need to specify the exact bit width, since the bit width is embedded in the instance declarations of that class methods. Next, I explain meta functions in the HAR-BMI. Two meta functions generate types and accessors. The first one, the generate struct, takes a structure name and list of member names, and generates data types and functions and instance declarations for accessing the specified members. The generate symbol resembles generate struct, but it generates variables instead of functions. These two meta functions report an error if a member or variable symbol does not exist in the guest OS. And as seen in the two usage of meta functions, HAR-BMI does not generate code for all members and variable symbols. This is our design choice, so I will discuss it later. So, in addition, HAR-BMI provides meta operators that go back and forth between a structure and its member. The right arrow operator obtains a member pointer from a structure pointer, and the left arrow does the opposite. And in these two meta operators, it generates the corresponding function name, this case PID of or PID2 task struct, from the specified structure and member name. In addition, these three meta operators that expand to multiple procedures are available. The first one, right star arrow operator, calls the right arrow operator, and then reads the value at the obtained member pointer. And the next, the double arrow operator takes a list of members instead of a single member, and it generates an appropriate sequence of the right arrow and right star arrow operator for the specified member list, and finally obtains the member pointer to the last member. Lastly, double star arrow operator resembles double arrow operator, but it finally obtains the member value of the last member. In the last, HerBMI provides a meta function that converts a variable symbol name into a Haskell variable. This is a get symbol meta function, which takes a variable symbol, and it generates the corresponding Haskell variable get init task from the specified variable symbol. By providing these meta functions and meta operators in prior threads, the programmer need not directly use the generate types and accessors in their programs. Based on the design in the prior threads, I'm going to show how BMI statically detects the errors in libBMI. For a C1-like error, this task underscore struct is misspelled as task struct, which the underscore character is missing. For this type of error, the generate struct meta function signals an error that notifies the absence of such structure, as in here error message. And for C2-like error, in this case, it obtains the structure pointer from the member pointer, whose the direction should be inverted. This type of error was detected by the Haskell compiler, since it is a mismatch between the argument type of the generated function by the sprites in here, which has a type of PID of task struct, and the type of init task, which is a task struct. Lastly, the possible C3-like error is that passing the 32-bit integer to the print8 function, which takes an 8-bit signed integer. This error is also detected by the Haskell compiler, since there is a mismatch between the argument type of print8 function, which is int8, and the type of PID val, which is int32. This, as seen in the previous slides, C2 category of errors that miscalculating addresses, and C3 type of errors that using incorrect bit widths cannot occur in HerBMI. This is because the generated types and accessors hide address calculation and bit widths from the source code. As I mentioned it before, HerBMI does not prepare all types and accessors for all data types in the Linux kernel. One of the benefits is that there is no need to include a huge code for numerous structures. In fact, the Linux kernel defines over 10,000 structures and its many members. Another benefit is that the explicit declaration of C names makes HBMI programs clear and easy to understand. On the other hand, there is a drawback that every HBMI program should specify every C name accessed from the program. In spite of this drawback, we judged the drawback as not critical and adopted a dynamically generative approach. Based on the design choice in the previous slide, we developed HBMI in 2 phases. The first phase is that defining the types and accessors needed to run example programs. In this phase, the types hold C-type information that enables HBMI to statically detect the use of different type addresses and values. In this phase, the Haskell's static type checking mechanism was quite effective. In that second phase, we provided concise notations for HBMI programs. The defined meta functions and meta operators simplifies program portions that were inconvenient to write in the first phase, and the metaprogramming facility by template Haskell was quite practical in this phase. Also, template Haskell helped the building of HBMI, but there are some difficulties. Difficulties was appeared when we wanted to define a meta operator that took the Haskell variable instead of a structure name, like this. Unfortunately, this is impossible to define because template Haskell does not support querying the type name of local variables. The type name of local variables is essential to define the right arrow operator since it is needed to generate the corresponding function name. So we finally defined the meta operators so as to take a structure name as in here. All right. In this talk, I pointed out the 2 problems that two problems in an existing virtual machine introspection library. There are 2 problems here, and these problems are alleviated from the perspective of programming languages. This is done by creating a Haskell library that uses static type checking mechanism and the metaprogramming facility. Also, we implemented programs that coped with the rootkit in the Linux guest OS. If you're interested, please see our paper. That is all for this talk. Thank you for listening.
Questions for Takato?
Last question about the Haskell implementation. I think it's a pretty cool thing that you can generate all of this template Haskell. Helps you in the ways that it has here. But more a question about VMI in general. How does one actually go about identifying the locations of these structures within the guest image, given that, you know, it's, if that's, if, you know, don't worry that that's too out of scope, but
identify. Sorry. Well, sorry. Can I hear what identify means?
So, you know, you were introspecting on data structures within the image of a guest, you know, and it seems to me like that's not necessarily an easy thing to do, and I was wondering in general how that is done. I know that's not to do with your library per se, but if you have any insight there, that'd be interested. It's okay. it's quite all right as well.
Sorry. It means offset and addresses. The address of variable symbol and the offset of the member in the structure was determined by the JSON file, which generated from the debug information of Linux kernel itself. So by querying, by retrieving the offset and address from the JSON file, we can determine we can calculate the address and offset from guest OS.
So it's statically knowable from the kernel image then, I guess, is the, yeah, okay.
Yeah.
Cool.
Sorry.
Thanks.
Thank you.
Any more questions, anyone? All right. I think that's it then. Thank you, Takato. This is the end of the second session. The next session starts at 4 p.m. So see you there.
So hello everyone, welcome to the demos talk, demo section. So we have 2 demos and then we have 1 and maybe more lightning talks depending what happens in 1 hour. And the first demo is by Yuhi, Shishu and Yingying about an auto-parallelizer for distributed computing in Haskell. Can go.
Hi, good afternoon Haskell community. We're here presenting our auto-parallelizer for distributed computing in Haskell. I am Yuxi Long, or Jaden.
I'm Shiyu Tony Wu. Hi.
Yeah, and I'm Yingjie Dennis Xu.
Yes, and a little background on our project. First of all, we are undergraduates at Duke University, and this is a project that came as part of a course project. It's from a distributed systems course, to be exact. And we had no prior functional programming experience before this. We just had this crazy idea, and then we self-learned Haskell and coded up this prototype in a month. And so why I'm saying that? Because we want to hear your criticism and feedback on this project, on where this could go, on what are the limitations you think this have. And so please take everything that we say with skepticism, with criticism, and we'd love to hear your feedback at the Q&A section. We'd love to hear what you think. So the motivating question that we have is, can we take a single-threaded program and gain some parallel speedup for free? Well, the main issue that arises is side effects. So what if for example, what if 2 processes use a same temporary file? Then if you parallelize them, they will run into each other, right? That's the main problem with why you cannot randomly distribute processes, functions to be run to be concurrently run. And in distributed computing frameworks like MapReduce and Apache Spark, which are industry frameworks for industry-scale distributed programming, they usually require 2 semantics for the functions that are executed. The function's side effects need to be atomic and idempotent. What is atomic? Atomic means that the side effects, if you have 2 programs running at the same time, the one side effect, you cannot get you have program 1 write, program 1 read, and then, let's say you have 2 programs that increment a counter. If the programs are atomic, that means you cannot, the programs read and writes cannot be interleaved. So basically, each program's transaction, this cannot be further broken down. That's what atomic means. Also, the side effects need to be idempotent, means that if the program is executed more than once, the side effects will remain the same. And as I described it, these 2 semantics need to be kept track by the programmer. And I want to introduce what options do we have to parallelize the programs in Haskell? Well, we have the par monad, which is a monad that distributes function calls. And we have Cloud Haskell, which is a backbone for servers and things to communicate with each other. And the thing is, they require user annotation for each line that you want to parallelize or each function you want to parallelize. What we're trying to see is, is it possible that we parallelize programs with little user annotation? And by little, I mean close to none. The core idea is to use the notion of pure functions in Haskell. As a refresher, pure functions are functions that have no side effects, so there will be no external input or output. And pure functions can be executed or computed in parallel as soon as input variables are ready. This thing is impossible to identify in object-oriented languages, because it's not required, it's not enforced from the lowest level. So you can call on a library, you think that it's pure, but it actually somehow it writes into some temporary file or something very down into the branch, very down into the execution depth. But it's easy to identify in Haskell because we enforce the purity. Just look at the type signature. A pure function and a pure function has a very pure functional signature, and the function on the right is possibly impure, although I say possibly because maybe monad is also a kind of monad that happens to be pure. The idea is that we can parallelize pure functions whenever possible. Sounds a simple idea, but we couldn't find any implementation online or anywhere, so we built one.
Yeah, so I'll go ahead and talk a little bit about the underlying architecture and how this is actually implemented. So the high-level idea is that we take a generic Haskell program and we parse the main function, and then from that we try to build the abstract syntax tree from that, and then so imagine it will look something like that, tree on the right. And from that we can tell a lot actually. So for example, for this line, what we want here is we want to know what are the data dependencies, and so for this in this case we have that this add function depends on two inputs A and B, and indeed the function returns a value that is in turn assigned to C. So we kind of C actually depends on the result of the function. So this is kind of what we need. From this tree we built this data dependency graph, and based on this data dependency graph, we have a greedy scheduler that looks at which nodes have all their dependencies ready, or they could have just no dependencies at all, and then we run them in parallel. And then when they return, we take the results, right? And then we mark those nodes as ready, right? And then, so for example, in this case, if A and B are finished computing, then we can basically schedule C because we know that all of its inputs are ready. So there are many limitations actually with how we implement this prototype, and we made a lot of assumptions. So the first one is that we consider each line as a separate job. So this is kind of one of the main issues with this approach is how do we determine the granularity of these jobs? And we have some ideas that we'll talk about later. But so with the current implementation, so for example, it will be like a line like this. For example, let x equal to f of AB, where AB are the inputs to f, and then x takes the result of is being assigned to the result of f. In our case, we are only working currently with, as Jana has said, pure functions, and we consider it ready, which basically we want to schedule it as soon as it has all of its inputs computed. And our scheduler sends all these functions with their inputs to these worker nodes, and then we expect them to finish computing, and then when they're done, they send results back to us, back to the master node, and then we basically go from there. So our approach kind of differs from a lot of the existing work in the sense that we implemented it with a multi-node system in mind. So we're kind of a distributed system approach. So our abstraction is basically at the network, like computer node level. So our workers are spawned by the distributed simple local net package that we used. And here are some of the main limitations of our current prototype. So we have no support for monadic operations. We have very limited support for higher order functions. And one of the main drawbacks that we have right now is there's no inherent fault tolerance mechanisms built in. So we expect that this is definitely something that needs to be done for this to be more scalable. So by fault tolerance, we mean that there's a lot of inherent unreliabilities, both in the network and how the worker nodes execute these functions. Sometimes some workers are just slow and things like that. So we'll elaborate more on this in a bit. And lastly, right now the limitation is that the user kind of have to define kind of an interface for serialization, deserialization kind of manually for the functions that they want to use. And this is, you can think of this as something very similar to the, protobuf for RPCs.
All right, so next I'll talk about the experiments we did on this prototype. So basically the type of task we consider is we're just generating some very large random matrices. and then we would just like multiply them together, and then at the end we'll just like add up all the entries in these results. And in particular, we kind of considered two different types of granularity levels. So on the left we have the fine grained level, which is basically I think it's like a step-by-step walkthrough of what this task is. But then we also have the coarse-grained type of the workload for essentially the same task. But in that one, we kind of put some of the operations in a bundle, and then that gives us a more coarse-grained type of workload. And what we find is that so the speed up that our prototype brings is actually significantly affected by the serialization overhead. So this is something we observed from the experiments. Because on one hand, we see that the coarse-grained tests, they achieve very, I would say they achieve very good speed up because it's very near the shared memory parallel. But then on the other hand, the fine-grained tests, they are very slow, and we think it's because of the large serialization overhead. And here are some of the figures we find. So, so on the left, again, we have the execution time on the y-axis and the job size on the x-axis. So you can see that across all job sizes, when you increase the number of workers, the execution time just decreases, and then it approaches the SMP. And then the one on the right basically shows the execution time versus the number of workers. So you can see that as the number of workers increases, the execution time decreases quite a bit. Yeah, so next then we'll talk about our some future directions.
Yeah, so here are some of our ideas for where we think this project could go in the future. So as I just mentioned, one of the main ideas was to add fault tolerance. So and kind of on top of that, we also want to implement some kind of strategy for straggler mitigation. So this is a common technique used in some of the other kind of frameworks that we already mentioned, like MapReduce, where because for some reason some worker may just be very slow in running its particular task. So towards the end of the execution stage, we might want to schedule some redundant tasks so that and we can finish execution faster. And indeed, they were able to show that this is empirically true. And we also want to kind of maybe implement something parallel for the multi-core system. So for this, we are thinking about doing something where we can kind of somehow analyze the program and then construct a similar tree-like structure that where we can reason about the data dependencies, and then from there we can figure out kind of where to put it the annotations for example using the par monad, and then we can generate a program from there that can in turn be run on shared memory processors. And one of the main limitations with our current approach is that we have big overhead for serializing and deserializing from whether it's large matrices and such. So our idea here is to maybe use some kind of binary format, like for example the .pickle format in Python, where the overhead is much less. And we also had an idea here to enforce coarser granularity in the sense that if we have a set of independent tasks ready at this stage, we can actually kind of merge them into a single task, send them to be executed on a single worker, and then when the result gets sent back, we can then kind of destructure the response and then kind of figure out which one is the corresponding result of execution for each specific task. And lastly, we also want to be able to support side effects, and would imagine, for truly maybe for scalability, this would we would have to kind of interface with some kind of external APIs or external infrastructure, like some kind of distributed database where we can kind of write the intermediate results, maybe similar to how how MapReduce did that and how Spark, they did that with their RDDs. Yeah, and that's all we have. So yeah, again, we are we're students, and we are we're not experienced in any sense in Haskell or in distributed systems. So this is just kind of an idea that we had for a course project, and we we really want to hear like kind of what you think of this, like, and yeah, just really any feedback is welcome. Also, I guess if this project is useful at all, or like where we could kind of take this in the future. Yeah, thank you.
Satnam Singh, Grok. It's great to see people working on Haskell and distributed systems, a matter close to my heart. I've got some suggestions for actually future work and reliability that you mentioned. So really big distributed systems, they achieve all these nice properties we want for things like replication, load balancing, they're orchestrated. So what could be a cool direction might be to go in the direction of like Kubernetes and trying to make a connection to an orchestration system like that, so that you could get a balance between using an existing framework, which explicitly has aspects that are explicit, and marry it with the implicit distribution that you're trying to discover. So it's not a question, it's just a recommendation of one direction to look at.
Thank you so much. Yeah, I think we definitely thought of that, and we just didn't really have the time to experiment with Kubernetes. But yeah, we did kind of thought of like scheduling it instead of kind of putting it in a Dockerized environment and kind of schedule instead of to be running inside these pods on different machines. Because Kubernetes handles a lot of these kind of load balancing automatically, and then it's a orchestration, container orchestration system. So yeah, I think that would be very nice to kind of for us to use in the future. Yeah.
Armando from Mercury. So you mentioned like Hadoop and Spark as an alternative, but have you considered using parts of what you've built to run on like that sort of infrastructure? Because there's a lot of nice things about it, and lots of companies have like these old HDFS clusters, and they're just terrible to program on because even Spark's not that great, and the Haskell options are also not good. So have you considered like going that route?
Yeah, I think that's, so I guess, originally what we thought is to really kind of be able to kind of help run any Haskell program. So in that sense, I guess there are some things that it's just not inherently possible. But I think we did think about other ideas of like, I guess, writing something that more high level, and then kind of like how SQL works on top of like, for example, PySpark, and how these execution engines, right, they translate SQL queries into concrete algorithms that can actually get run. So I think we did also have some ideas like that, but I think if we were to make this work with Spark, I think we have to be very specific with what kind of user programs, maybe more like heavy on data processing, more explicit about like I think that's also definitely something that we can look into. Yeah.
All right, cool. Thanks.
So Simon Jones, Epic. I'm apologetic that I didn't make the beginning of your talk, but maybe you've already answered this question. But how do your the components of your distributed system, how do they communicate with each other? How involved is the programmer in orchestrating or describing that communication? I mean, one distinction might be they barely see it. It's just as if there was a big shared memory. Another might be it's like Erlang, you send messages, or it might be somewhere in between.
Yeah, so our implementation actually, so with our current prototype, all the user needs to do is pass in the profile, like, passing in the program with .hs, some kind of .hs file. And then, we handle
So it's fully implicit.
Yeah, truly implicit. Yeah. We handle everything for
So the tricky thing about that then is that it's, the cost model is a bit unclear, right? So if you need, if you're going to execute f of x over there, and x turns out to be a terabyte data structure, then there's an awful lot of data to send across your distributed fabric, right? So have you thought about whether you might, how you might give the programmer some control over what gets done where?
Yeah, I think that's, we haven't really thought, to be honest, we haven't really thought a lot about that. We did realize that, like when large amounts of data get sent around, it's quite tricky to still make sure that it's still performant and the overhead is not too large and it doesn't really kind of, offset with the, the speed up, the parallel speed up. And I think we'll definitely kind of look into
so
that.
Kind of experience report then from the past,
right,
like 20 years ago. This is really hard, and we basically failed, right? So
you
you may do better than us, but it's really tough.
For sure.
So some Either you need to have some extremely high bandwidth mechanism, I don't know, remote DMA mechanisms or something, where you're very close to the network, you're very systemsy about it, or else maybe you need to get programmers a bit more involved in a bit more like Cloud Haskell, perhaps, which was very explicit about, it's really adopting the Erlang model. That's the other end of the spectrum. Or maybe you could do something in between. But just trying to say, we're going to have a big, shared memory across the planet, and we're going to automatically make sure all of the data appears in the right place at the right time. I don't think it'll ever work. I think it's too hard.
Right, that's for sure, yeah. I think, over time, I think we'll probably move to somewhere in between. Right. I think you just mentioned.
Over time, I would start soon.
Yeah, thank you.
Hey, very cool project. I guess a similar question, so with something like PAR, you only get the programmer specified parallelism. With an approach like yours, there's very fine-grained parallelism, but I think there's a risk that the sort of concurrency overhead overwhelms the parallel speedup. So have you thought about how to whether there's a happy medium where you can maybe the programmer and the system can work together to not parallelize every call to plus.
Yeah, I think that's for sure. I think kind of like what Simon mentioned. I think it would be nice to let the kind of programmer have some say over what chunks of the program they want to be paralleled, and maybe they know that for example, they wrote something like some map function and some fold R or fold L, then obviously that a lot of that could be parallelized. So I think we will that's a very good direction that we should definitely look into, and we will.
Cool.
Hi, Ben here with Summer of Haskell. Very cool work. I'm wondering if your implementation right now takes into account laziness at all. Like, one of the great benefits of Haskell is the ability to compute things lazily. So as a simple example, a function which takes 2 parameters, second one is inordinately expensive, first one is really cheap. The function just returns the first argument. In that sort of case, does your mechanism protect and make sure that you don't accidentally send the second argument to its own process that takes a million years only to just return the first argument?
Yeah, that's a good question. I think we did saw some like previous work that were kind of more focused on trying to figure out like doing some kind of analysis and trying to figure out which functions are actually lazy, and a lot of it was very heavy on static analysis. And our current approach, we're strict right now, so we don't really take that into account. But I think we can definitely try to incorporate some of that work to see if we can kind of to try to determine if. But I think that a lot of that work is more low level, so I expect it to be quite challenging. But to integrate this in this kind of thing,
At a certain point, you're just like running a synthesized Haskell on top of Haskell to figure, like, at the end of the day, you might just have to compute it to actually figure out what needs to get computed, which ruins the point.
Right,
But very cool, thank you.
Yeah, thank you.
Do we have other comments or questions? No? Good. Thank you very much. Very good work. Good. So in the next demo, we have Makoto telling us about verifying Haskell rewrite rules.
Okay. Yes. So, hello, I'm Makoto Hamada, coming from Gunma University, Japan. So this work is about rewrite rules in GHC. So GHC has a feature of user-defined rewrite rules for optimization. For example, this map rewrite rule translates nested two maps into the single map, which can be regarded as more efficient than the two maps. So GHC applies this kind of rewrite rules to core program in the simplification process of GHC compilation. So, and these rewrite rules has been proved to be very useful in many libraries whose efficiency often depends on rewrite rules. But there's no formal theory of rewrite rules so far. And moreover, no rewrite rule checker has been developed for more than 20 years since the initial proposal of rewrite rules in the GHC in Haskell Workshop 2001. So in this work, I want to improve this situation. And this work is actually about how to ensure, how to ensure correctness of rewrite rules using term writing theory by giving rule correctness theorem, which I showed. And to rigorously prove this theorem, so we also need suitable rewriting schematics of Haskell. And to give this, so we give a calculus called system FRE, which is roughly extension of system F omega extended with rules and equations. And we also provide a prototype tool called recheck, implemented as a GHC plugin that accepts real Haskell program and checks rules on the core programs based on my theorem. So I'll show you this in this talk. So first, to identify the problem in current GHC's rewrite rules, so let's consider this simple program. So this involves one rewrite rule that translates, that rewrites an expression f of something to the integer 1. But in the program part, there's a function which always returns 0. So what is actually the output of this main? The answer is actually output 1 because that by enabling rewriting feature in GHC, so GHC firstly rewrites this part to 1 in the desugaring simplification process, so the output becomes 1. But this can be considered as wrong. So this rule is wrong because in principle, rules should not change the original meaning of the program. So we want to address the correctness of this kind of problem in this talk. So, but actually, there are several levels of correctness of rules. So first, I'll show you 3 levels of correctness. The first is about termination. So this is the most basic property to ensure to avoid compilation failure. So in rewriting theory, this is known as formalized as strong normalization of rewrite rules, which means that any computation rewriting passes are finite. And the second is about well-definedness. So unlike function definition, rewrite rules may provide an ill-defined function. So for example, this is a legal descriptions of Haskell's GH's rewrite rules. But so we cannot predict what is the output of this main, because in GHA there's no particular rewriting strategy is assumed for applying rewrite rules. So this may be 0, maybe 1, or maybe undefined. So rewrite should be well defined, meaning that in rewriting theoretic term, rules should be confluent and strong normalizing. So this also gives a unique normalization property. And the third is about meaning preservation. Rewrite rule is called meaning preserving with respect to a program P. So if instances of left and right side by ground substitution theta have the same value evaluated by the program P. So this means that given a rewrite rule, we can have an instance of rewrite step by substitution theta. Then in this case, both terms must have the same value. So this is meaning preservation. So in rewriting theoretic terms, this is often called inductive theorems. And among these three properties of correctness, the relationship is as follows, that the meaning preservation implies well-definedness, which also implies a termination. So in this talk, I define the meaning preservation as a correctness property of rewrite rules. And because this is the most strict notion of correctness. And also note that this also means that to prove meaning preservation, we also need well-definedness and termination. So both of these are also important to establish meaning preservation. So next, let's consider another example. So this is a well-known append function, and this involves a one rewrite rule for associativity of append. So this is actually rewrite rule. But this is one of the typical use of rewrite rules coming from natural property of data type. And in this case, correspondence of rule is nothing but to prove that this equation holds under the assumption of this program, considered as equation axioms. But in this case, logically, actually, equation logically, this is not a theorem of first-order equation logic. So what kind of equation hold is that actually ground instance, so all ground instances of this associativity holds under the assumption of program P, so these regarded as equational axioms. And usually, so this kind of associativity on list is proved by using structural induction. But formally, adding a structural induction rule to equation logic is known to be not complete. And so not only this reason, but anyway, so in this work, I choose another approach by not only relying introducing structural induction, but so we just use rewriting property to deduce correctness of rewrite rule. So we establish the rule correctness theorem. This says that given a total Haskell program P and rewrite rule, suppose that a program P considers rewrite rules with the rewrite rule to be checked is local confluent and also strongly normalizing. Then this rule is correct with respect to the program P. How this is proved is that as follows. Let theta be a ground substitution. And then we can have a actual rewrite step of this rewrite rule, L2R. So in this case, so we try to calculate the normal form of both sides, both of this rewrite step by using a program P. So they must have the normal forms of both terms because we have assumed that this is strongly normalizing. But these two normal forms may be different. But so in this case, consider that this D and D dash is connected by this rewriting passes, meaning that these are convertible. And we have assumed that this is locally confluent and strongly normalizing. So by Newman's lemma, this means that this is confluent. So we can have, by confluence property, we can have a common result of D and D dash. And also by using the totality assumption of the programs, so D and D dash are not constructor terms. So we cannot, so these can't be written by further, so these must be the same. So this means that this rewrite rule is meaning preserving. So this is approved. So next I'll show you how to apply this rule to check the correctness property of associativity of pen. So in this case, first we regard these programs, this program as a rewrite rule. And so rewrite rule is, again, just a rewrite rule. And then it's not difficult to show this rewrite system is strongly normalizing. Because this is basically just a structural recursion, and this just moves the parentheses from left to right. And also, we can show that local confluence by using so-called critical pair analysis. So critical pair means that a critical situation that may break a confluence. And the critical pairs can be enumerated computationally by just checking the left-hand side, checking the overlaps of the left-hand side by using unification. So in this case, we can enumerate this. So there are actually 3 critical pairs, and all of them are joinable. And so what this means that, for example, this first critical pair, this means that associativity and the first rule is overlapped because so this excess may be nil. So in this case, so this part can be rewritten by the first rule, but this time also can be rewritten by applying associativity, but this can be rewritten to this part, so this makes joinability. And all of them are joinable. Then in rewriting theorem, it's known that if all critical pairs are joinable, then we can conclude the local confluence. So both of these assumptions are satisfied. So we can conclude that associativity is correct by the theorem. And so this next example is about the map-map fusion. So in this case, in programs, there is a definition of map and composition. So in this, so again, we regard these are rewrite rules. And rewrite is just rewrite rules. And in this case, strong normalization of this rewrite system is not so straightforward because there is a function argument. But by using a suitable reducibility argument, we can show that this is strongly normalizing. And also, again, we can show local confluence of this rewrite system by enumerating critical pairs and checking joinability of all of them. So in this case, again, there are 3 critical pairs, and all of them are successively joinable. So for example, in this case, this shows that there are situations that the overlapping between map fusion and fast map rule, because this excess may be nil. Then so this part can be rewritten by the first rule, but we can also apply the map fusion, but both becomes nil by the first rule. Then so two conditions are satisfied, so we can conclude that the map rule is correct with respect to the program by my theorem. So, but to more precisely state this argument, so we also need a more formal, more formal semantics of GHC's rewrite rules. But currently, it seems that there's no formal semantics. I just found in the GHC users guide, there's informal semantics. It says that matching in the GHC rewrite rules is matching modulo alpha equivalence, alpha conversion, and eta expanded if necessary. And if more than one rule matches, then GHC will choose one arbitrary. So this means that this is almost the same as non-high order rewriting system. But in this case, this must be polymorphic. And also, which also means that polymorphic part should be considered to be a polymorphic lambda calculus. So we propose a new system of RE, with the extension of F omega with general high order rewriting system. And sorry. But so before stating the system FRE, so we need to review how GHC itself is formalized. So GHC is formalized as by using the system FC, which is roughly extension of system of omega with let and case expressions. And in GHC compilation, any source program is translated to core. So core is equivalent to system FC. Any program is translated to core. And actually, rewriter applies at the level of core, not to the level of source program. So we formulate that system FRE is an extension of system omega with rules and equation. And we don't use let and case expressions. So what actually this means that, for example, so this is a Haskell program involving rewrite rule. And in the compilations desugaring process of GHC, so this Haskell program is translated to this core binding, which is at the binding whose right part is usually a lambda expression involving case and sometimes red, like this. And the rewrite rules are just translated to rewrite rules on core expressions. Yes. But in system FRE, so we regard everything is translated to rewrite rules. So which means that we don't, instead of using case analysis, we use this pattern, we keep this kind of pattern matching definition of rewrite rule. And also this red binding is also lifted to top level rewrite rule. And rewrite rules are just a rewrite rule, but on core. So, so this means that in system FRE, everything is rewrite rule. So which also gives a rewriting semantics of Haskell program. So I think that this is a bit similar to the spirit of Bass calculus mentioned yesterday, Simon Bento-Jones, which also chose a geotic system by considering everything as Lie roots. So this shares a spirit of, so our work was spirit of the Bass calculus. And so we have implemented a prototype tool based on system RE, implemented the GHC core plugin, so placed here. So this actually, our tool is called recheck. Recheck handles the core expression after descheduling of Haskell program. So this means that, actually, so recheck consists of translator from core program to rewrite rule, and the conference checker, and the strong normalization checker, and the correctness checker by our rule correctness theorem. And so this means that, so to obtain this rewrite rules, the actual process is not to translate from directly the source to this. So we actually translate this type of core program to the rewrite rules. So translate the this kind of translation. And the conference checker is based on critical pair analysis, but in this case higher order. So we needed to we implemented the polymorphic higher unification to check create critical pairs. And the strong normalization checker is based on a new criteria called polymorphic termination guarantee based on reducibility argument. And coexistence is by our theorem. And note that so we have implemented so these techniques, actually simply typed version of these techniques in my previous tool called SOL, which participated recently international conference competition and termination competition, and which actually won in both competition in recent years. So this means that so these techniques use the current state-of-art technology known in rewriting community. And yes, then, so we have applied recheck to check the actual Haskell program. So many Haskell programs. I report several results. So, and as I have shown that append and map example, for this example, recheck automatically check the correctness of the rules. And we can also consider the case of maybe a leader of some kind of monad with monad rows. In this case, monad row can be checked automatically correct with respect to monad implementation. And we can also prove the correctness of this kind of rule and also show the strong normalization of some complex rewrite rule. So by these experiments, so theoretically rechecks works well, but okay, but there are several actual technical issues in the implementation of recheck. So I actually, so one is about module loading in GHC. So I don't know actually how to collect all relevant modules and all the source codes or paths of used to the modules. So in practical, so I have tried to apply recheck to practical using program. So usually program depends on many other modules. But so we couldn't currently solve this issue, so we can't collect all relevant modules. So I should resolve this. And another is about the built-in functions. Built-in functions, so in this works, so as I should say, all program must be related to, translated to rewrite rules. But built-in function doesn't have definition, so we cannot translate this to be rewrite rules. So this is problematic because to checking joinability of critical pair, we need to rewrite an open term, which may involve built-in functions. So we may need some partial evaluation or something like that. But I don't know how to combine partial evaluation and rewriting technique. And yeah, some more specific implementation is, I don't know. Actually, I'm not actually an implementer, so I haven't yet understood where the core is internal representation. So I must resolve. But actually, what I want to say here is that, so I actually need help of someone. So I'm actually looking for collaborator, or postdoc, or maybe consultants, so to help to resolve this kind of issues. So if you know if you know some good idea to resolve this, so please tell me and ask me. Yeah, that's all. Thank you very much.
This is very impressive. There's a lot of way to walk between rewrite, like typical first order rewriting, and system F omega. There's higher order polymorphism, etc. I'm not necessarily aware of the latest developments in rewriting theory, but like, so I don't know how much you've had to work, but like, what was the hardest in this? What caused problems technically?
So technically, so one technical issue is that at the levels of types, so high order rewriting is rather actually different from first order rewriting. First order rewriting is well established, but the high order rewriting is much difficult because of to calculate critical pair, we need a unification between rewrite rules. Right. But in the higher case, we need higher unification. And at the levels of polymorphism, we also need to take care of unification of polymorphic terms. Mm-hmm. So, but technically, these are not so very difficult. But usually, rewriting theorists are not interested in this kind of practical applications. For example, Haskell. But I try to correct relevant theoretical results. So system F, rewriting, high order, unification, something. And then so I build a system F army.
And what is the strategy? Do you try to eliminate higher order and polymorphism?
No, I don't eliminate. But,
so you play directly with it?
I need to extend suitably, theoretical soundly, the known results of rewriting to at the level of higher order polymorphic case.
Okay. That's very impressive. Thank you.
Yeah, indeed, impressive. A quick question. The system requires the program itself to be already terminating to do something? Or what happens if I have non-terminating Haskell code and I want to pass it through your system? Will it be able to do something with it?
Could you say again?
So, sorry. If I understood the slide correct, then you need to prove strong normalization for program plus rules.
Yeah, yeah.
So what if the program itself already isn't strongly normalizing? Do you still get some useful signal from the plugin, or will it just not accept?
Yeah, in this theorem, so we assume that the program must be strongly normalizing. So non-terminating program is not accepted. But we can also give so I forgot to say that I have also a draft paper on this subject. In that draft, I also show that we can also accept non-terminating program, which is not relevant to checking rewrite rules. So, but this itself assumes a strong normalization. But we can also refine this theorem that accepts that may involve non-terminating function in P, but which doesn't affect crucially to prove the correctness of the rule.
Okay, thanks.
Any other questions? Okay, thank you very much.
Sorry. So finally, so I have uploaded a draft paper on this subject in my homepage. So if you are interested in, please look at. Thank you.
Good, thank you. And so this is the lightning talk. Okay, no. We have one. Nice, but we don't have a laptop. Okay.
Would you like to put on mic, or would you like to hand it? Mic. Is anything happening with this?
Yeah. But how? Works?
Okay, who in the audience maintains a Haskell package more or less actively on Hackage? Okay, there's like 2 or 3, so basically you, the audience. This is just a small thought on, well, the thought is really, we painted ourselves in a corner where we do all this maintenance of dependency ranges, and I think it's a lot of work, and it seems to be more work than what we achieve. I don't have a solution for that problem. But I thought it would at least be nice if, some dependency of yours gets updated, that you have to do as little as possible. So ideally, you do nothing, or something tells you, well, there's a new version. Should everything be automated? And they did little things in that direction. So let me show you what you can play around with if you want. So the first thing Shall I make? No. Okay. So yeah, sorry for not using my own laptop. This means there's a slight delay, but it should be somewhere here. No. Ah, there was. First piece that I wanted to show you is not very surprising. It's a GitHub action you can add to your repository, and once a week or whatever you configure it, it will run Cabal outdated, look at which packages have new versions that are not supported by your library, and we'll create a pull request to propose updating that. Now that's nice and easy, right? It's like one step that takes the pain away of upgrading. But there's an interesting problem here. Imagine this tool runs on your repository, or maybe you don't have the tool, but somebody comes along and is very nice and creates a pull request updating the upper bound on a dependency on your package. And your CI is green. What do you do? Say again? Quick merge. That's wrong. Do you know why that's wrong? Okay, so I'll paint this in the room here. So you have your packages here. Your package foo. You depend on A and also on B. Now A gets a new version. You allow the new version of A, or somebody else in a pull request allows the new version of A. But maybe B also depends on A and doesn't allow the new version yet. Now CI runs, Cabal, the dependency solver, looks at all dependencies, finds out, oh, I can't use the new version, I'll use the old version. CI is green because you haven't done anything new, but you click the button and you merge it, and then maybe later B gets the new version, and then actually people are able to use the new version of the dependency together with your package, and it may break. So this is the first thing to be aware of. You can't just merge a green PR, which inherently sounds like we're doing something wrong. If it's green, it should be okay. Otherwise, CI is kind of broken. So there are two little more pieces I can. Yes?
I didn't understand anything you just said, but it sounds.
Okay, I'll do it once more.
I need a more clear. Maybe I don't need it, but I don't understand what goes wrong.
Okay,
Is it written down anywhere?
Yes. There's a section here. Okay, basically what I just said, for those who want to read along, is this. Can I make this? Is it Option plus or Control plus or Command plus to make it larger on a Mac? Command plus. Thanks. Okay, your package depends on bar, and with an upper bound. And now you also have some other dependency. And now a new version of bar gets released. Now the question is, can you allow the new version 1.2 in your package? So you create a pull request, you run it through CI, and it may turn green. But this does not mean you've actually tested against the version you allow, because the constraint solver may not pick that version for other reasons. And if you now merge this pull request updating the upper bound, then then you might have a problem. Okay, maybe the problem comes clear when I show the solution. Or
CI has some memory, right? If you clean
it's not because of that. It's independent of the cache. It's really Cabal is trying to figure out a set of packages for which all involved packages are happy, and that may not include the version you are trying to test.
Because you may depend on that, which depends on bar 1.2.
Yeah, that's the last line there. Yeah, precisely. Was there a question there? Okay, so the first thing it's actually the second thing chronologically, but that doesn't really matter. So let's see. There is, press the right button. So one way of approaching the problem is, the problem is the upper bound to Cabal means any version below is fine. But really, when you're running CI, after you just updated this bound, you really want to run the latest version in your CI. That's the thing you want to test. So one little tool that I created is Cabal force upper bound, which does what it says. Here's a little example. You run it on your Cabal file, and it gives you a set of constraints you can pass to Cabal that make sure that you really run against the upper bound. So you could integrate that into your CI system as like one of the cases in the matrix. And then if somebody bumps the upper bound of your dependencies and the pull request turns green, then it is safe to merge. Yep, question? then the pull request will be read because Cabal will tell you I can't find a solution, which is precisely what you want to have in this case. Okay, so this is already kind of useful maybe to some. If you want to be really pedantic, and I mean we're Haskellers, you might notice that it's not just the upper bound that may be a lie. Let's say you've upgraded your dependency a few times, you've always updating the upper bound, you're changing the code, you still claim in your Cabal file that you support version 0.1 from 5 years ago, maybe. But you've probably changed your code, you've maybe changed how you use that library. So if somebody now tries to use the latest version of your package with an old version of that thing for whatever reason, it's quite likely that it breaks. And if you don't want your Cabal bounds to be a lie, in the sense that you're claiming to work with something that you're not actively testing, then you need to put in a little more effort. And there's another tool and action and so on you can use here. It's called Cabal plan bounds, which relieves you from having to touch Cabal bounds in your Cabal file completely. The principle is, like, what I just described as a problem, like CI is not testing what the bounds are saying. You can just turn around into a solution and say, the bound should always be what you're testing on CI. So if you use this tool, which combines the build plans from various CI jobs, so you run it against multiple versions of GHG, on multiple stackages, multiple these things, it collects all the build plans and calculates the bounds of what you are actually testing. So we can see this in action in one of my, okay, this was the wrong, how do I get to the, no. Oh well, I can just navigate by clicking. Maybe. I can't find the URL bar. It's okay. I'll click. We're in full screen. It's fine. It's actually better this way because then people can follow the mouse, and that's more friendly for the audience. So don't worry what this library is about. But if you look at one of these, the CI for maybe the latest commit, then it runs a bunch of configurations. You can see the upper bound, which is the one I showed. And then there's a last job. And if you look at the matrix, you'll see it depends on all the previous ones. Where do I get the? So yeah, you can see that follows all the other ones. And there it takes all the Cabal bounds, all the build plans, and calculates the Cabal bounds from that. And then does it actually say something useful here? Probably just says no, it's because it's up to date. It doesn't say anything here. It would update the pull request to change the Cabal bounds to what they should be, according to what you have tested. This wasn't prepared, so maybe it wasn't fully clear, and happy to take questions. But I thought I'd share it to you that we can have this thing here. Sorry. Maybe I can show you the Cabal file that comes out of this if I'm. So you get rather systematic bounds where these are precisely the versions that I'm testing this on CI, and therefore they're more. Oh, this is a feature of Cabal since a few years of saying this version or any version where the PVP implies that it should still, the package versioning policy. So that this still works. So basically it's larger than this, larger or equal than this, but smaller than the next major bump. There's a short syntax for a range, and there's little, yeah. Okay, I just thought I wanted to share this to the crowd. Any?
There's sort of like 3 to the 4 combinations. I know there's a lot of potential combinations.
That's true.
You've actually tested all of those.
Not all combinations, but at least. Yes, correct. The cross interaction between dependencies is something that I did not address here. This, which.
Can Cabal even express that?
You could probably express it as like a big set of alternative dependencies with flags or something. Probably. Okay, so. the question was whether the solver would have problems with so many disjunctions. Yeah. If everybody would do that, if that would be a problem, I don't think it would be, because I think even like a normal range, Cabal just treats as like trying one after another. So it shouldn't make a big difference. And yeah.
Will humans still be able to resolve any dependency issues without just slamming around you on everything?
Will humans have problems with that? I don't know if this is really much so much worse than a range from 0.1 to 0. Okay, to 0.10. Just listing the intermediate ones. Okay, I guess Ben didn't. Did you have a question, or you were moving towards the microphone?
Sorry.
I don't want to miss your question.
So much the comment, but because the point of Simon's point of, well, you're not being all that picky, and that is true. And in this case, I think that's fair. But just for everybody else in the room, we had in the Haskell community at one point the package matrix builder, which actually did attempt to build sort of many combinations of package versions and make that information, which plans are feasible and which actually build, available via web interface. And I think that is an area which it sounds like a really nice approach that never really panned out. I think largely implementation reasons. If somebody won a project, I think it would be a great contribution to the community as a whole. Let's pick that up again.
Yeah, cool. Indeed. Yeah, sure.
Slightly off topic, but how do you have 275 repositories?
Just get as old as I am, and then it just accumulates over time. It's like wrinkles in the skin. It just comes after a while.
And give some lightning talks to help you.
Well, also just noticed I had one statement to make, and already was 3 repositories involved, so you can easily inflate it. Okay, anything else? If not, then, well, thanks.
Thank you. Okay, so let me, since my laptop is up, let me say,
Oh no, yeah.
That.
Is it? Let me see. HDMI.
Yeah,
I
but
can just...
let me just show. So there is another. I don't know what's going on. But there is another session. There is this. There you can just go. I am using the chair. This.
Because both of them are there, it's getting feedback. Using the chair.
No, the chair is mute. Okay, now.
Which one do you want to use?
The chair. Yeah, I just want to say that there is another session of Lightning Talks tomorrow at 12. And if you want to register, you can go here and just write your name here. We already have one. And today we're going to have a second lightning talk by Ben, correct?
That is right. Yeah.
Good.
Apologies. This was actually.
That's yours.
This
And
is
that's
all right.
mine.
I'm just right here. Apologies. Let me just turn this off for just a moment. No, there we are. Okay, you can hear me, right? All right, great. So yes, today I would like to just talk a bit about some of the work that we've been doing in GHC to improve the test coverage of our backend. This isn't necessarily going to be new to anybody, I fear, but it nevertheless, I thought there's some lessons that we have sort of gleaned in the process of this work, and I'm rather happy with the outcome. So I thought it would be appropriate to sort of share here, given that could use some talk. So yeah, first we're going to start off with some sort of role playing here. So if you imagine for a moment that you're a compiler engineer working on a functional language compiler, and one morning, as you often do, you wake up and come down, start reading your email, and you see a ticket. Like many tickets, or unlike many tickets, this actually sort of starts to bring shivers down your spine. The first word, you see the word incorrect, and then UTF-8 decoding. And this is, incorrectness, actually getting the wrong answer. Well, this is actually quite bad. Crashes, the user has some idea that something has gone horribly wrong. If the program actually does terminate, this is not actually working, is it? Here? Thank you. Okay. Is that? No. Can you? There we are. That's a little bit better, I guess. Is that better? Yeah. Okay, great. Right. So, crashes are something that users it's unpleasant. Incorrectness is essentially arbitrarily bad. Turning positive bank balances into negative and this sort of thing, which users tend not to appreciate. So you, looking through this ticket, start to wonder, this looks quite unpleasant, and you start to think a little bit about why this might be, and of course, play around in GHCI, reproduce the issue, and start thinking a little bit, and you start thinking about where this problem could lie, and of course, thinking about the size of the program that you're trying to debug. It's a little daunting, right? I mean, GHC itself is a multi-100,000 line piece of software. But thankfully, we all know that it's well engineered and composed, as many compilers are, in sort of a pipeline, right? We can start to think about individual pieces in isolation, and they have well-defined interfaces in the form of intermediate representations. Now, for a long time, GHC dealt with testing sort of going from parsing all the way down to object code, right? And making sure that the object code that arose from a particular compilation, from a particular source program, was sort of consistent with the expected semantics by way of just compiling and then running, right? And that's where most of GHC's test coverage comes from. We have a test suite of many thousands of small modules that we run, or at least compile, and we make sure that we get the expected outcome. But that approach, obviously, as we see from our ticket here, doesn't always catch everything. And in fact, as we know, testing large systems like compilers is quite difficult. So how can we do better? Well, thinking about sort of the context of our ticket here, we know that recently GHC merged an ARH64 backend, and in fact, this ticket manifests on ARH64. So maybe that's the reason. And we can look at our diagram here and say, okay, so this ARH64 backend is in fact this box right here. And so we expect that this is going to take in, this box takes in C++, one of the intermediate representations of GHC, one of many, and it's going to output assembler. And so maybe we can actually just focus our testing efforts on this bit here. And so now instead of having to worry about trying to generate, or if we want to take a randomized testing approach to finding the ticket in question here, that we don't need to worry about generating random Haskell programs that might generate that manifest the program, but rather we can worry about just generating C++ programs. And then we could potentially think of ways that we might take advantage of randomized testing and assert that the programs generated have the expected C++ semantics. So this is, in fact, what I did. Now, you might think, looking through the GHC's AST, the C++ type of expressions, is actually quite straightforward. So you might think, okay, well, how bad can this possibly be? Of course, if you look here at this middle constructor here, this is really, this constructor is doing quite a bit of work, right? This is the Mach-op constructor, which of course carries a Mach-op or machine operation value in it. And this is essentially an enumeration of all the primops that GHC supports. This is when you write add int hash in your Haskell program, what is going to manifest, this Mach-op constructor is how this primop is going to manifest in the back end. And of course, there are many, many primops here. So the question is, how do we go about actually testing that these things are doing what we expect? Well, around 2 years ago, on a cold October morning, this sort of situation, this ticket that I point to here, actually, I was the one on the receiving end of this, and I was faced with these questions and realized, well, the current testing infrastructure that we have, given that there are so many more backends that we are either adding or have added in recent history, we really need to do better here. And so this gave rise to this test primops package, which you will find on GitLab. And of course, it is an implementation of essentially a quick check style test suite for C++ programs and a simple yet fairly descriptive description of C++'s expected semantics, particularly currently focusing on its expression language. Moreover, it provides how do we actually go about testing C++ programs? Well, of course, we need a few things. We need a way to generate programs. We need a way to compute the expected result of a particular program. And we need a way to run the program against GHC's actual backend and evaluate its result. And that is what test primops provides. So to sort of very quickly go through how we start to think about C++ programs and their semantics, well, we can start by thinking about what is a number. Well, numbers in C++ are actually a bit tricky because C++ is, of course, a low-level language, and numbers in general are just bit patterns. They aren't real, certainly not real numbers, nor are they necessarily natural or integer. Rather, they're bit patterns that have particular meanings to particular operations. And this is a case where we need to be quite careful. While multiplication, for instance, may interpret a number as signed, and addition may interpret the same value as unsigned. And so we need to be explicit about both the signedness and the width of our literal numbers. We can then generate programs, which again, we're going to be focusing on the expression subset of the C++ language. And expressions, of course, are going to consist of the various primops that there we are. Nope, there we are. The various primops, which we can write explicitly as a gadget, of course, indexed on its width, the width of the result, as well as memory operations, relational operations, and literals. And we might think that, we can pretty easily write a generator for this in quick check style. That's quite straightforward. The shrinker is less so, but we'll pass over that for a moment. Of course, then we pretty quickly find that the compiler is more clever than we'd like, right? So we can write 1 + 1 as a test program, but that's not going to get anywhere near the backend. GHC is quite clever, even in C++, at simplifying constant expressions like that. And so we need to take care to introduce constructs in our expression type that will hide the inside, the structure of expressions from the simplifier by way of, for instance, taking, placing the result, the value behind a memory access, or by way of some explicit opaque primop. We can then define semantics of our language. This is actually something that was incredibly useful in that C++, being a rather old language, and having diverged quite a long time ago from the original paper that defined it, had quite a few, and continues to actually have quite a few infelicities with that paper. There's still sort of an active effort to define what we actually mean by C++ programs, but currently working on this. And we can then write, given our interpreter, our pure interpreter, from expression to the result of that expression, which is of course just a number, we can then write a more generic form of interpreter, which of course may accommodate I/O, since we will need to run compilers when we're going to actually evaluate this C++ program via compilation. And then we write the means of doing precisely that. So we emit the C++ representation of our test program. We can then compile that with the tested C++, which may be different from the tested GHC, which of course may be different from the GHC that we used to compile test primops, the actual test suite driver. And that's actually quite important, because we need to ensure that if a bug is, we may be testing a buggy compiler, and if we test a buggy compiler using a test suite that itself was compiled with a buggy compiler, we may not actually see the failures of our buggy compiler, right? The infelicities of our of these buggy cases. So we have really two compilers relevant here. We have sort of the compiler that we are using to compile the test suite, and the compiler that we are using to compile the test cases, and that is the compiler, that latter compiler is what we are actually testing. We can then finally execute our, the object code that results. That is a bit of a tricky process, but this allows us, we will sort of leave that as an exercise for the reader, but that gives us an interpreter, a compilation-based interpreter, which we can then compare against the interpreter that we previously had, the pure interpreter, the reference interpreter, if you will, provided by the test suite driver. We can then write a very simple property of agreement between these two interpreters on the interpretation of a particular expression, and that allows us to deploy quick check and all of its wonderful tools against compiler bugs in C++. So was it worth it? Yes, absolutely. We've had actually, I think over a dozen bugs, issues so far have been identified in various C++ backends, the native code generator primarily, and nearly all of these have been fixed. So there are, of course, quite a few tricky cases. Conservative approximations, in particular, require special treatment. Things like the mul-may-o-flow mock-op, which tests whether a particular multiplication of two operands overflows the word size. This is something that the particular C++, the code generator, may actually opt to be conservative in its result and say that things may overflow when they in fact do not. So that, of course, you have to be careful to define the semantics of these operations correctly. But there's quite a few other things that you can do once you have all this infrastructure. And so, in particular, we found it was very useful to be able to check foreign calling conventions. If you do have a foreign call to a C function, for instance, via C++, this is an area where, on some platforms, this is quite tricky to get right. And another area where we have found bugs. This is something that we've implemented, and it's been quite useful on Darwin in particular. Checking floating point operations is, of course, rather tricky and requires particular attention when since we need to worry about what constant folding may do as well. This is actually in progress. Sven Tenney is currently working on this, who's a contributor. We have an effort on foot to start checking the imperative fragment of C++. This is, of course, quite tricky, but there have been issues which we recognize this current approach, which focuses on the pure subset of C++, will not catch. And finally, we actually handle cross-compilation as well. This has been very useful when testing the JavaScript and WASM backends. We don't discuss this here, but anyways, that is that. If you are interested in contributing to test primops, the project is on GitLab, and thank you for listening.
A very quick question.
Arno Spivak from Tweak. It's a quick question. I'm not sure the answer is quick. My intuition when you started speaking about semantics was, we are going to run two different backends, one against the other, because we're testing bugs in primops. It's very unlikely that they have the same bugs. So you chose to instead implement reference semantics in addition to what already existed. Why?
likelihood of finding bugs there, thank you, is actually quite high. And the reason for those bugs is almost certainly that, the two authors of these backends probably did not agree on the semantics of the language itself. I thought it would be a useful, and it was, in fact, a very useful exercise to myself go and think about those semantics and try to figure out, well, if we were to start afresh here and decide and document the intended behavior of C++, what would that behavior be? Well, needless to say, there are many more cases than I initially expected. This is actually rather tricky, and there continue to be cases which we have not defined or are trying to decide on. But having a clean Haskell implementation of those semantics has been very useful in reasoning. And we have now typically, we hope that this is going to be sort of the reference implementation against which backends can be written going forward. So that's, I think, maybe the...
That answers the question, yes.
Great.
Thank you very much.
Hi, Alex Radul, Google. I wanted to ask, so you found bugs. How does the process of locating where the bugs are in the backend and fixing them compare to fixing user-submitted bugs?
The problem with user-submitted bugs is there aren't that many of them, but we know that there are bugs in the compiler. There's first the difference of we actually can easily identify, and with relative, it doesn't take a lot of computation to actually find a good number of bugs with this model, despite the fact that programs you're generating trees, and of course that scales pretty poorly. There are a fair number of, especially in light of recent additions to the GHC, a good number of low-hanging bugs that we quickly found. Now, as far as fixing those bugs, once you have identified them, it really isn't that different, except for the fact that instead of having to manually reduce the test case, which in some cases can be very, very difficult. If we look back at the ticket that we saw here, we have a very simple program, but behind that decode UTF-16 LE, there's several thousand lines of code, or at least several hundred, if not thousands, lines of code that you need to sort of sort through, and eventually, it's only clear that something bad happened between GHCI and the printing of that result. And there's a lot of code implicated there. Whereas in a test primops model, you have, you can rely on shrinking to, you already start with a relatively small failing test case, even without shrinking. Then once you shrink, and we put a fair amount of effort into the shrinker, you can get what is essentially the minimal test case very, very quickly. So it really has reduced the amount of time necessary to identify these sorts of issues precisely by drastically. It's been quite a difference. Does that help?
Yeah. So the follow-on question.
Yeah.
When a user submits a bug, you know that that bug does actually occur in real programs, at least one real program.
Yeah.
What kind of confidence do you have that the bugs you find here are worth fixing?
Well, that is a good question. And in some cases, some of these bugs I know could not occur in real programs unless the user explicitly used primops that they, there are some cases, some of the undefined cases in particular that we're still trying to work out are actually in programs which the user would need to write explicitly using unboxed types and primops directly. You cannot actually with lifted Haskell, the nice integer int, for instance, the int type, you cannot write a program that would trigger this sort of undefined behavior. That being said, I think in general, ensuring that we have a well-defined semantics for C++ is actually a useful enough exercise, and a good number of these bugs most certainly were reachable, so from Haskell code.
Yes, thank you very much. So we are out of time, and I feel bad for the student volunteers. So let's stop the official session, and you can keep the discussion after that. Thank you very much.
Thank you.